what I wanted to talk about today was meshing. Um, I've got an actual model here. So what I'll do, I'll start to play around with the model. Like I've told you guys before, I've got my slides over here, so I'll make sure to touch on everything. And if anything does need a bit of help, I'll make sure to go back to it and play around with it as well. Right. So what we'll do, meshing geometry. So what we'll do, we'll just play around with this and we'll start to talk about what we can do with meshing, right? So the whole reason we're generating a mesh is that we're going to perform our stiffness calculations on the actual mesh, and the mesh quality and the size will be very important when it comes to picking up the accuracy of the model. On the left hand side, so you'll notice I have a part. I've got multiple bodies inside them. They're all unconnected, and we also have what's called a multi-body part here as well. All right, so this multi-body part, and it shows us because we've got a part it's got multiple bodies in it. It will be sharing nodes across the actual interface as well, which can be beneficial depending on the situation. And we'll talk about that and how we can get to that as well, and how we can play around with it, right? On the meshing side of things, so we did touch on this yesterday. I have global controls for the mesher, and I also have local controls for the mesher, right? So by standard, this is what it comes up with. It's got these default sizings. What I'll do is I will just focus on, let's just focus on this part for a second. We can right click on it and generate the body on that particular part. You'll notice I've got the sizing. So this adaptive sizing over here is often Ansys's first guess, right? It just tries to figure out, based on the geometry, curvature, things like that, how big should the elements be? And it's a fine, good guess to begin with. We can increase the resolution here, and you'll find that the elements will start to get finer and finer. And that might be okay, and we'll do that for the first pass, right? There are some couple of options here, but I'll generally leave them as is. Afterwards, what we can do is play around, turn off the adaptive sizing, and we've got a couple of more options here that we can start to play around with, right? So we can clear the generated data. Now, what happens is that these global settings will apply for everything. So I can generate a mesh on every component, and it will look at whatever the global sizing is, right? So at the moment, we don't have any controls for capturing curvature or proximity as well. And again, you'll notice, some of the actual elements are pretty large, right? You'll notice this element size here. So depending on the actual domain size, it'll try to guess how large, these elements should be. You can zoom in. Let's just say we want to apply a 30 millimeter sizing. We can clear the generated data and do it again. And again, so these are global controls, right? So it'll just, based on these controls, it'll try to determine what an appropriate mesh might actually be. All right, so we'll let that generate that real quick. Yeah, so you can see what's happening here. Now, we definitely want to go in and start to make some changes to the actual geometry, right? What we can do though, so if we wanted to globally make some changes, we can insert things like capture curvature, and I will clear and generate the mesh. And as it's generating the mesh, as it's kind of talking about, so it's going to look at areas where we've got curvature, radiuses, and it will start to apply more elements, right? So you can see we've got a couple of options. We've got the minimum size here, so that's how small an element can be, and we often play around with this normal angle as well, right? So this normal angle, at the moment it's around 70 degrees, so it will actually put one element every 70 degrees as well. Right, so we've got two ways that we can kind of control what's happening around that region. So if we say clear everything else, let's just hide and just focus on that. You can tell this is a very small element. It clearly needs more. Instead of, that minimum size isn't really hit though, right? So if we zoom in, you can notice, the elements are considerably larger, but that's because we've got this normal angle here causing some problems, right? So again, it's restricting elements every 70 degrees. And in this particular case, if we start to make this angle smaller and smaller, you'll notice that the elements get smaller and smaller until, it gets to the point where it will hit, the 0.3 millimeter value. We're still pretty far off, but this is one of the ways that we can do it. Now, the problem with doing it globally, we'll generated on this one, is that we might, refine this really well, and that's awesome. But then we can get to the point where we can start to over refine certain regions, right, that we just may not be that interested in at all. So the global region and the global sizings is great to begin with, but generally we'll go in and then make some specific mesh requirements to get a high quality mesh around some of these regions, right? So we'll do exactly the same as well. So that was curvature, right? So I'll turn that off for now just to illustrate the point. Now the next thing is something like proximity as well. So again, if we hide all the other bodies, we'll just focus on this part. And if we generate the mesh, we'll see again, so proximity tries to put elements between either the edges or between the faces as well. And again, you'll notice we puts 3 elements across it. We've got some parameters here, again, 0.3 minimum sizings. We've got a default of around three elements, and it's putting it between the edges and the faces as well. So you notice here, where the edges are, present, it'll put 3 elements, but in the body itself, it's a relatively coarse grid, right? Because we don't have 3 elements. Well, we've got 3 elements through there, right? So again, depending on what you want to do, we can start to play around with these types of things. Again, the problem can be, though, if I was to generate something like this and I was to generate the whole body, it can really cause us some problems, and it can start to really increase our mesh count. And if we were to take, a section through there, let's get to section 1. All right, we can see we've got 3 elements through there as well. And sometimes that might be what we're after. It might not necessarily be. If we've got very thin sections, right? This is a pretty bulky part, which is pretty good. But if we've got some thin sections, you'll notice again, it's trying to put a couple of elements in there. And we might not necessarily need that level of fidelity as well, right? Even though we don't have curvature, it's putting 3 elements across where all these edges are, right? So generally we'll use, the global sizings maybe to get some of these bulk shapes, and then we'll start to play around with the local size controls as well, right? Okay, so the first thing that we'll focus on is the component on the left-hand side. So I'm going to take, remove curvature and proximity. I will generate the mesh to begin with, and we'll just have a look at what's happening around some of these regions, right? So you'll notice, by the way, on the bottom left, just telling you how long it's taking. It's relatively large. So now instead of, instead of making the whole thing finer, if I select it using my body selection filter, I can right click and insert a sizing. And you can see here, it's telling me it's a body sizing. The default sizing at the moment is 30 mil, but let's make it 10 millimeters instead, right? And I can click on that and generate the mesh on that selected body. Right. You'll notice, it'll take a little bit longer. You'll also, if you kind of move around, it will highlight where it's actually meshing. Sometimes you can identify where some problems might actually be as well. And you can see the general mesh around here, right? So we've got some problems around here. Maybe we've got some very thin elements. If we wanted to have a look at the actual element quality, we can look at the display settings. We can have a look at the element quality. We'll see where we've got some very, there you go, we've got some very thin bad elements around some of this region. And maybe we were talking about before, why I harped on about making these really good, making high quality geometry is because in this particular case, we've got geometry where we've got quite a bit of problem areas, right? And so this is something that hasn't quite been fixed up, right? And again, you'll notice around here, it's trying to put really bad elements across all these edges, right, that we haven't removed because we haven't taken it into space claim. Now, I always recommend take it back to the source and fix it at the source, right? So we don't persist with these problems. But we've got some techniques that we can use in order to fix this up, right? So we've got some body sizings. We've got in order to reduce the element count. We can visibly see where we've got some bad quality. And if we were to take a section, so let's just hide everything else, by the way. We use this section view. If you can't find it, by the way, at the home, it's up here. Or if you always forget, at the top right, we've got a quick launch setting. Just type in section. It'll give you indication. Or if you go take me there, it'll actually go to that context. So let's go back to section. I say take me there, and it'll just indicate where exactly I need to be. All right, so there you go. You can take a section. Look through the section. I've got my elements showing as well. and you can select that, and you've got this little indicator here, and you can move it around, do a bit of a sweep just to understand what's happening. Now, it's important to have a look what's happening on the outside as well as internally as well, because we want to have good elements again on the surface as well as internal. If we have bad elements, we can start to generate stress concentrations around some of these regions, and we can start to have some problems with our actual results, right? So it's always recommended to have a look at your quality. The other way to have a look at it is if we go to our quality section over here, we can look at the mesh metrics and we can turn that on. So let's just say we have a look at the quality again. All right, we can drag this up. And generally we want to be above 0.1. So if we left click on the bar, you can actually highlight where you've got these bad quality elements, right? It's where we've got all these bad quality elements. All right, so a couple of things we can do. We've got some body sizings on some of these elements, but maybe we want to go in and add some local sizings around the face. So I can select this face. Let's just say we want to focus on this region. Now, normally we'd go in and probably start to defeature it, but for the sake of this argument, let's just add a sizing. Let's use my line. I can select the edge at the top and the bottom right. It'll give me a length. So let's put 2 millimeter elements around this region. You'll notice when I change it to 2, the circle actually changes size as well, right? So the large circle that you can see is 2 millimeters. And if we zoom in, that small circle is around 1.5, and that's that D feature size here as well, right? So now that we've got that, let's go in, let's just regenerate the mesh, and let's just keep an eye on this region as well. So you'll notice what happens that we start to refine a little bit more around that region using that 2 mil face size. If we say make it 1 millimeter again, and we'll generate the mesh, right? You'll see that we've got smaller elements. All right, give me 1 second, guys. I think we've got a couple of people on the other chat that doesn't have a link to this current meeting, so I'm just going to send them a meeting link. Just give me a tick. You'll notice, by the way, the elements get a little bit smaller to capture the regions. All good. So what I was saying, so we can use some sizings around there. The other thing that we can do regarding sizings is, so I can select my body, my face. I can also go in and, select a specific edge if I wanted to as well, and insert a sizing. Instead of element size, I can actually start to play around with some settings. So I can specify the number of divisions, and I can say put in 5 divisions, and it'll try to put in 5 divisions around that region, right? So 1, 2, 3, 4. We've already got around 5 actually, so I'll just stop it. We'll go in and put 10. We'll set this behavior to hard, so it'll try to enforce that actual condition instead of it being a soft constraint. Right. And then the other thing you'll notice as well is I've got these, so now it's gone in and added more elements. I've got global controls for curvature and proximity, but in the actual local sizings, I also have local controls as well. So I can specify, I want to pick up proximity around here, between this edge, and I want to put 3 elements across there, right? So it will put 3 elements across this edge, depending on how many elements that we've got and what the sizing is. So the minimum size is around 0.3, so it's just going to put 1. So I might need to go in and select my face sizing, make this maybe 0.1 instead, and regenerate the actual mesh, right? So I wanted to show you guys, we've got global controls to generate a high quality mesh. It will influence the whole object. It will influence everything. And we've also got local controls as well. So I can specify sizing on the body. I can specify sizing on the face and the edges as well. And then within those controls, I've got some advanced features, and I can locally change my curvature or proximity settings as well, right? So again, you'll notice now it's, again, a couple more elements through there around some of these regions. And again, I've got some more constraints through there as well, right? So what I'm going to do, I'll leave the body sizing, but I'm going to delete it. The other thing that we can do is that, we've got some problems with some of the CAD around here. So, I might want to tell it, I don't want you to actually follow, the edges and put elements around there, right? So we can insert what's called a method, and we can specify some different methods. We'll be having a look at them in a little bit second. Have a look at tets. And instead of patch conforming, so instead of conforming to the edges across here, I want to make it patch independent. I'll get rid of the body sizing. Because I can specify body sizing here of around 8 millimeters. All right, we'll put no for now, and we'll just have a quick inspection of what the mesh looks like, and then start to make some changes. So let's just hide everything else, and we'll give it a second to generate a mesh. Right. One of the questions that also gets asked as well, and we'll be talking about hex meshing in a little bit, that gets asked quite a bit, is depending on the complexity, what type of element is the best to actually use, right? So this is often a good graph that I try to pick up. Generally, what happens is that when we've got a pretty complex geometry at the top, it can be very difficult to generate, a high quality hexahedral grid. We've got formulations like the multi-zone, which I'll talk about later on, that can help us out, but it can be quite difficult. Whereas at the bottom here, we've got some geometries that's regular, that's sweepable, that we can, push across an axis, and we can really cut it up as well. So, it does come down to a little bit of experience, understanding at what point is it worth it just leaving a tech grid, what point do we need an actual hex grid as well. Hex grids are generally more computationally efficient. So if you've got a grid full of hexes, it'll solve a little bit quicker as well. So these are just things that you want to be kind of considering. There's no easy way to go about it. It does require a little bit of trial and error. Right. All right, so with the patch independent, you'll notice zooming in, again, it's just kind of walked over some of the radiuses around there, right? And if we have a look and check out the element quality, if we bring up the graph that we've got at the bottom here, you can see the element quality. Previously, the minimum was around 0.1, and now it's above below 0.1. Now it's above 0.1, so that's very good. And most of my elements, are relatively good quality as well. Right. Again, we can go into the patch independent methods though, and we can start to play around with them, right? So locally, we can apply things like refinement, and we can turn on, say, curvature as well. Maybe instead of we'll leave it at 13, 30. We'll have a look. As we're doing this, by the way, if you go to the mesh tree at the very bottom, it will show you as well how many nodes and elements that you have, just in case you want to keep an eye. You want to make sure these nodes are within a limit. All right, so we'll let that generate that mesh. All right. So you'll notice it is taking a little bit longer. If you zoom around, you might be able to see roughly what it's working on as well. Right, and I guess it is because we do have quite a bit of curves around some of these regions. Right. The other thing that I've been doing, by the way, is what's called selective meshing. Right, I can select a specific component when it's not meshing, and I can generate on that specific component. We can move around to other components as well. And this is generally how I'd start with something as well. Maybe tune in the global settings to make sure it captures the broad features that you're after, and then focus on specific specific components using your local sizings as well. While that's generating a mesh, one of the things that I'll show you guys is exactly how what's happening with some of the mathematics kind of behind it. So you can see here for the elements, we've got displacement degrees of freedoms that are solved on the actual nodes. And internally, we've got Gauss points. These are the integration points, sorry. So we've got stress and strain that's calculated on the actual integration points within each of these elements, right? So we've got displacement at the end. We've got stress and strain internally, right? So remember our static equations, we've got some sort of force, some stiffness matrix, and sort of displacement. First step you can see here is that we're calculating displacements at the nodes, right? So we're just rewriting this matrix. The second step, we're calculating the strains on the integration points, and from the strains, we're calculating the stresses. So this is another reason why it's important to have a high quality element. If you've got distorted elements, we've got, we can potentially calculate, incorrect strains, which will give us incorrect stresses as well. Depending on our analysis as well, it'll determine how the stresses and strains get interpolated to the nodes, and we look at what the node values are, right? So if we've got a linear analysis, the stresses are simply extrapolated to the actual nodes, right? So they're extrapolated out. Whereas if we have a nonlinear component with things like plasticity, they're simply copied over from one to the other, right? So depending on what type of analysis that we're actually conducting, right, the way the nodes the displacements get calculated, the stresses and strains then get calculated, and then how they get extrapolated to the nodes or whether copied to the nodes, does come into play as well, which is why getting a high quality mesh is very important. So you'll notice around here, we've got a considerably finer mesh around some of these regions. And the benefit of doing it this way is that we don't have to go in and sometimes fix up some of the geometry. Sometimes we've just been given the geometry and we don't have the opportunity to fix it. We can see that we've got, better mesh around some of these regions. So I'm just going to go in and I'm just going to turn that off. So let's have a look at some other geometry as well. All right, let's have a look at some of the other methods. So I'm just going to focus on this for the time being. Oh, wrong one. So let's focus on these elements for now. All right, so if I generate the mesh here, we'll just have a look at what there you go. So this is what the default quality looks like. That's clearly not acceptable for any of these components. Right. So let's start to make some changes to it, right? So let's go in, let's just focus on one particular case. One of the things that we can do is, again, add some local sizings, right? So we'll locally add a sizing of around 5 millimeters, and then we'll have a look at what's happening around this region. All right, looks a little bit better. In this particular case, we've got what's called a sweepable object. So we can go right click, and what we can do is we can show, sweepable objects. Let's just show everything. Let's see if we can pick that up. So we'll do that again. So let's clear the generated data. Right click, show sweepable objects. Objects there. We can definitely sweep this one as well. We just have to do it a little bit of a different way, right? So these methods here, remember, if we were to just generally generate the mesh, it just creates a tetrahedral grid. So what we can do is insert a method. And just like before, one of the methods that we can apply is this sweep. And this sweep, let's just try and give it to it and see if it'll figure it out. No. So the sweep, what I wanted to do is take the face here and I want to sweep it across that radius, right? You can see it tries to figure out, what the automatic faces are, but sometimes it can have some problems. So let's give it a manual source. So I'm telling it this is the manual source to have a look at. And let's see if we can actually generate a mesh on something like that. So again, it's still having some problems. So instead, I'll give it a manual source and a target, right? Again, there's no easy way. Sometimes it works, sometimes it doesn't. And we'll see what it looks like. I have a feeling the sizing is a bit too large. Oh, there you go. So it's able to generate now a high quality, hex mesh for me. It's taking that face and sweeping it all the way across there from that radius. In the sweep method, I've got some more options as well. So based on the sizing, that's how it's determined the dimensions. If I go in there and give it, a 2 millimeter sizing, we can see that we've got some finer elements across there as well. I can go in, again, I'll change it back to 5 mil. And in this particular case, I'll enforce, I want 20 divisions. So I want to sweep 20 divisions from there all the way across, right? So I'll have, 5 millimeter sizings around some of these regions, relatively large. And I've got 20 divisions across there as well. Right. So sometimes we've got geometry like this that can be swept along an axis or swept kind of through the axes as well. And we can start to play around with it, right? So we can, we could do exactly the same for this. Actually, let's see. Yeah, so it doesn't quite, let's hide the other bodies. So we need to go back then and start to apply some of the sweep methods as well. You'll notice because it's a multi-body part, it is sharing nodes across the actual across that interface there. So the nodes here are all lining up. So what we might be able to do, maybe let's just try give it another sweep and see if it's able to figure out, what's happening there. All right, it doesn't quite work. So we can go in, then afterwards we'll hide this body and hide the other two as well. And we can manually go in and specify the source, right, as well as the target, and then generate the mesh, show everything, and we'll have a look at what's happening. All right. So again, we'll go in and probably we need to add some sizing. Right. How do you select the proper method according to the shape? So there's no, it comes down to a bit of trial and error, right? There's no easy way to just look at something and figure out if it's going to work. In this particular case, you can look at it and you can tell yourself, all right, I can take this face. I've got a clear axes. I don't have any, holes or extrusions or anything like that. So that allows me to, implement a sweep method, right? I can do exactly the same for something like this, right? So if I hide everything else, again, I generate the mesh. That element sizing is a bit too large to begin with. So let's go in and specify a 5mm sizing and generate that. And what straight away you'll notice, because the geometry is able to be swept, even though I didn't need to add anything, I just needed to give it some appropriate sizings. You can see it automatically creates what I need to. I can again manually go in, give it a method, specify the sweep. And in this particular case, let's just say I only want 4 divisions across there, right? So I only want 4 elements, and I can enforce that as well down the line, right? So there's a bit of trial and error when it comes to it. You look at it, you have a think about it yourself. Something like this is pretty complex. There's no way I can easily sweep across a surface. I might need to do something in space claim where I make some fixes and cut up some geometry to generate a high quality hex grid. But in this particular case, it doesn't make sense, right? It makes sense just to leave it as TETs, right, using our patch independent methods. Over here again, you can see here, I did it the first time, it didn't quite work. I added some sizings and then some sweep controls, and I've got a high quality grid. And then I can start to refine around some of these regions. Right, you'll see again, you do it again, you forget to add the sizings, and this is what it's giving you as well. Right. So you need to play around with it. The first thing that you do may not necessarily work as well. Now, the next method that I want to show everyone is the multi-zone method, right? So we'll give it a multi-zone method. So the multi-zone method is a little bit complicated, but it's pretty powerful. So what I'd like to do though before is just showing you what we can do with it, right? Here you go. All right, so the multi-zone method, what it does in the background is that it tries to cut up the geometry internally and tries to generate some high quality hex grids, right? So there are times where the software is able to do it internally, and then there are times where it might fail, and we start to use some of these models to actually have a look at it, right? So again, it tries to decompose the box. We can specify source and targets if we want to as well. We can even specify multiple source and targets as well for this particular case. If we start to have some problems, we can again start to go in and start to play around with the mapped mesh type, right? So you'll notice here the difference. We've got hex elements over on the left, and we've got some kind of hex prisms on the right. So the hex is by default. Again, it just tries to generate hexahedral elements. And then every now and then, if there are some problems, it will put in, some triangles here and there on the actual surface mesh, which will be, extruded into prisms, right? The next thing that we do is the surface mesh type. So whether it's uniform or pave, I normally leave this one as default. I don't play around with this one too much. What I've found though is the local sizings. No, I've got another slide here. I'll have to show you. The free mesh type is something that I use quite a bit, right? As we're talking, so we're going to go over questions. As a general rule for what's considered appropriate sizing. Appropriate sizing, I'd look at this and ask yourselves, what do you want to actually capture, right? And that's what's going to tell you what the appropriate sizing is, right? If I've got, a fine curve around here, I want to capture, I want a couple of elements, right? Sometimes 3 elements across that feature, right? Across that, say, surface, in order to capture what's happening around that region. Sometimes you might put 3 in and all of a sudden you look at the stresses, they might not be appropriate, and you need to do a refinement study, right? So maybe you go in and add your local sizings and you put 6 elements across there and try to understand if the stresses change too much as well. Right. Again, something like this, if you're not that interested in what's happening around this region, you don't need a very fine size, as long as it's generally able to capture the overall shape. All of these elements might be unnecessary, right? So it really comes down to what are you interested in, and then also looking at the results afterwards. If there are stress concentrations around, the section on the right, then it makes sense to go in, make some changes to the geometry, and then run it again, right? So yeah, hopefully that answers your question. There's no, one appropriate sizings. It really comes down to what are you really interested in? And the more experience you get, the more you realize, what you can get away with, and the less iterations you take on creating a grid, right? All right, so we've got Prasad asking, so is useful the default mesh to coarse? Yes, so Prasad, yes, the default mesh is generally a bit too coarse, but is great for a first run analysis. I'll often just leave my very first run, get rid of all this stuff, up the adaptive sizing a little bit, and then make sure I've got my boundary conditions all in, right? Make sure I've got it fixed, supported, all my contacts are appropriate, nothing's flying about all over the place, right? I'll get a solution, and then I'll have a look at the results. Identify if there are any hotspots that I didn't anticipate, and then go back to my mesh and start to make some refinements and some changes around some of those regions as well. All right, so having a look at this, one of the things that I wanted to do in this particular case, so let's generate that. If we were to go in and specify this multi-zone method, and I'll need to go in and give it a sizing as well. Let's just say, we say select that edge, sizing is around 30. So let's give it around, say, a 10 millimeter sizing. Oops. Hide all other bodies, and we'll just have a look at what's happening around this region. You'll notice, the first thing that'll happen, it'll go wrong, right? So sometimes you apply a method and it just doesn't work, right? And we'll get a little bit of an error in a bit, telling us that we've got some problems with this, right? So that's when we go in and we know, all right, maybe we're going to go in and make some changes, right? So we've got some decomposition, so it's unable to cut up this geometry, right? You can go in and sometimes you can show what the problematic geometry is. Sometimes there's an edge or two that might be causing some problems. So what we'll do here is we'll leave the maps type. Well, we can easily go in and try and change it, right? So that way you can start to put prisms in the on the surface mesh, right? Just to see if that is something that we can get away with, right? So we'll let that play around with it. And sometimes we might find that maybe it can get away with it, but we need to have a smaller sizing as well, right? So again, there's no easy way to figure out from the very first go, looking at a geometry, what may or may not work. There is a little bit of trial and error in understanding and looking at something and saying, all right, this is the strategy or this is the technique that I might, use to get a good quality grid, right? Well, let's generate. Yep, so it's still causing us some problems. So what we'll do, we'll change this back to 10 mil. We will change this back to hexagon prisms. And what we'll do in this free mesh, we'll give it as tets, right? And we'll have a look at the actual geometry and figure out what it's doing, right? So you'll notice it creates what looks like a really good quality mesh on the surface, right? This is why it's important to take a section view through there as well, right? Because we've given it the allowance to create tetrahedral elements internally, that's that free mesh type. What it's done is that it's created, a nice, what looks like a nice structured grid, but in reality, we've got some pyramids that goes into these hex elements, these tet elements internally. There are some elements around here that are hex, right? So where it can do this type of mesh, it will try to generate that type of grid, right? So you'll notice, around that region, so around those curves, with some good quality elements. We can go in, right? Maybe the elements are a bit too large. Let's go in and make the element size a little bit smaller. And we can regenerate that mesh depending on what's interested. Now, in this particular case, say, Jimmy, going back to your question as well, maybe if this component isn't what we're interested in, we won't necessarily need to spend a lot of time generating a high quality grid. If there's no stress concentrations, not much is really happening at this particular component, you don't have to spend a lot of time generating a grid on, generating a really good grid on this, right? So, it can come down to also, for your particular way, understanding what is appropriate, what do you want to create, right? So again, you can see here, it's able to create a nice grid where we've got the rounds, but around some of these regions, it's still having some problems. Well, it's unable to, put some hex elements in there, right? And again, you can take a sweep through there, similar through there as well, right? The other thing you can do, again, you can then go in and start to play around with it. So instead of these tets, we can give it a hex core method. So this will try to put the hex core elements internally, right? This might be appropriate maybe for a part that's a little bit more bulkier as well. But we can have a look at the component and what it's generated, right? And we'll have a look at that. Right, so I mean, having a look through some of the slides that we've got, I think I'll just go over them relatively quickly. So we haven't talked about mesh connections and vertices. We'll talk about that in a little bit of a second. We'll talk about name selections as well. So maybe we'll have a quick look at that. But you can see here, so what this has tried to do is put pyramids on the outside and then try to fill the internal with some hex elements, right? So depending on what you want to do, that may or may not be appropriate. Right. So if you're not sure, have a look, generate it, have a look at things like the meshing quality, look at what the good and bad quality elements are, and then start to look around that region and what's happening around some of those conditions. Right. Now, the other thing that we haven't talked about, but let's have a attempt at that, is using name selections. Right. So previously I've been using the geometry here, and I've just been selecting the geometry components. Right. If I did, I can go and say select some, let's just say I've got these, these faces here. I can use, my name selections at the bottom. I can create a name selection from it. And let's just call this, curve 1. And then in my sizing, so let's get rid of that multi-zone. So I can suppress that. Let's just hide these other bodies again. And let's quickly generate a grid and have a look at the mesh around that region. Instead of selecting the face, we can use the name selection to pick up those faces and then generate it on that grid as well, right? So actually 5 mil is a bit too small. Let's just up that to 20. Make it a little bit coarser, right? We'll allow that to generate a mesh for us. Oh, suppress the wrong one. That's probably why. There you go. That should be easier for it to generate a grid. Bam. So we got a grid for us there. All right. So let's go in and let's just say maybe we made these name selections in SpaceClaim, right? We can now specify a sizing on the face, but instead of selecting geometry, we can go name selection. We can pick that face up, right? We can say, I want to give it a 5 millimeter face sizing, and we can generate that. Right. So again, we can go in and let's just say we can create, we can use a selection method in SpaceClaim to pick up all the holes of a certain size. Whoops, looks like it's closed down for me. That's good fun. So maybe we've used geometry to create, sorry, we used space claim to generate name selections for me as well. So I can use that, specify the sizing, and then generate a mesh for us, right? So let's go back to that. Let's just redo that. So actually, let's say select these, and let's just call it whole, right? Then let's generate a sizing on that whole, and let's give it a 5 mil sizing, right? And then on that particular component, I want a 5 mm sizing, right? And then we can generate it on that component. Right. A couple of things that we can do is we've got usability things like folders as well. So if we've got quite a bit of meshing components, we can start to make folders and bring all of them together. And we can use name selections in ways that generate meshes on certain components as well. All right. So there you go. So we've got a probably don't want a 5 mil sizing if I'm doing a 5 mil body sizing as well. That probably doesn't make too much sense, but there you go. So notice you got, course elements out there, 5 mil sizing around there. I mean, not ideal. The transition is pretty large, so probably not what I'd start with, but just to go to show you that if you've got name selections that have come in, you can use those name selections to generate a mesh for you as well. Right. Cool. So we'll have a look just through some of these things as well. So talked about name selections. We've talked about meshing methods as well, where it's appropriate to specify and use a hex grid over a tech grid. Right. So again, hex grids, we've got less elements and we've got a faster solution. Tech grids, however, the benefit is that we can capture these complex curves and these complex surfaces a lot easier with a better high quality grid compared to some of these hex elements, right? So, we've got pros and cons to each. We talked a little bit about as the complexity starts to increase on a specific component, we'll most likely start to be using TET elements, unless we want to be going in and then starting to make some, changes to the geometry and splitting up geometry as well. We talked about different methods that we can use. So we had a look at the patch conforming, right? So how it ignores some of the sizings and some of the defeaturing as well. So we didn't talk about that too much, but we can, if we've got something like this, again, I always recommend to make some changes, but we can use the defeaturing to get rid of that as well. We talked about some hex controls as well, things like sweep methods as well. So again, if we want to sweep across and sweep around a specific path. Again, some additional options. So if we have something like something that's very thin, we can give it a thin component, which will just put one element through the actual thickness. And again, you can see here, depending on what we've got, we can start to play around with it, right? We can even apply things like inflation around some of those regions. And you can see the geometry, right? Depending on what's happening, you might need to decompose that geometry in order to get a sweepable domain. Right. We then talked about multi-zone and what we can do there and how it can help us generate a good quality hex grid around some of these regions. And you notice through here as well. So again, you can sweep it through specific axes similar to before. So you can generate a grid and then sweep it through with specific element sizings as well. We've talked about selective meshing where we can mesh on a particular component first. If we've got what's called, the shared topology, you'll notice how we mesh it is important. So you'll notice over here, if we generate the mesh on the pipe first and then the block, it will take whatever face meshing is on the pipe and then use that as a geometry to create what's on the block. However, if we do it the other way around, as you can see, what happens is that it looks at the TET surface that's created. It's a sweepable body, so it's creating prisms, sweeping it across that surface as well, right? So depending on the geometry that you have, you can think about, what geometries you want to actually generate first as well. We can also go into there and keep it as a this is hide all the other bodies. We can actually keep a worksheet, of that process as well. So if you go into meshing, there's a worksheet. You can go through the different steps. So as an example, you can go start recording, right? So we will clear the generated mesh We'll go start recording, go back to our geometry, and let's just say we're adding let's just say we add a mesh sizing over here of 5 millimeters, right? So we'll generate that mesh first, right? And just to emphasize, we'll leave this as default. It'll be really bad, right? But again, it's sharing that element, that size there. Let's make this a sizing of around 2 millimeters, right? So again, you'll notice it'll share the nodes and it'll come out to 2 millimeters. And this one is most likely going to have a bit of a problem because it's trying to go from 2 millimeters on one end, there you go, to some pretty large quality elements there, right? So now afterwards, if you go back to your worksheet, you'll notice it's specify the mesh, the name, and the selection. And if you go to the name selections, by the way, you will see the name selections that have been generated, so you can change them manually. But the benefit it means is that if we go back and make some changes, if we've got the whole geometry set up using worksheets, we can regenerate the whole mesh as well, right? So again, and then we can show all bodies, and then we can generate the mesh on each of these individual components, or just as a whole, select them, generate the selected mesh, and it will generate it for us, right? So there you go. If we go to the worksheet, it's good to go. Now the benefit again is if I did want to go back and let's say I make some changes, this sizing instead, I want to make this 2 millimeters, right? Right click, generate the mesh. You'll notice it'll generate that first, right? Because that's exactly what we asked it to do. It will then generate the mesh on the right. It'll generate the mesh underneath, generation one on the bottom right, and then go through the process of generating everything else as well, right? So if you've got some complicated geometry that requires a couple of steps, you can use that functionality in there as well, right? We've talked about the global mesh controls and looking at things like curvature and proximity as well, and applying both curvature and proximity. I generally stick away from applying both of them to begin with, just because if you've got very small elements, you can get proximity that will over refine around some of these regions, and it will often blow up your actual mesh count as well. We can also apply things like growth rates. So I've left them as default. The default growth rate is around 1.5. But you can see here we can reduce the growth rate or even increase it if we want to have some more consistent elements around this region, right? Not really a huge amount, something we'll do for linear analysis, but if we have a non-linear analysis, maybe this is a rubber that's deforming quite a bit, around this area. We want to, have consistent, good quality elements around there as well. So we might reduce the actual growth rate around some of these regions, right? We talked about local mesh controls, right? So we've got all these different controls at the top. I think I forgot to show you guys as well. You can right-click, select something, or at the top over here in the toolbar, you can find exactly the same features around some of these regions. There are quite a bit of different, mesh controls. I've just walked through the main ones that we normally use, but you can have a look at the training and some of the training material and the tutorials, because there are, quite a bit more for some of the other conditions that you might have, right? So we talked about this, sizings. We talked about body and face sizings. We didn't talk about this, but we've got what's called a sphere of influence as well. So you'll notice, what it does, it just specifies a point and then refines around that sphere. So if we were, say, to take something like this, hide that, we want to give it a body sizing. And where this type here, instead of element sizing, we can give it a sphere of influence. We can specify, a radius for that. So on the global coordinate system, so we'll need a coordinate system. Let's generate a coordinate system here. Right, so it's generated one there. Body sizing, select that. Radius can be 10 mil. Right, make it larger, 30 mil, and we'll give it 5 millimeter elements around that region. Right, so again, in that region, it'll just generate a sphere of influence. Right, so maybe we'll make this one and make this a little bit larger, just to emphasize what's happening. Right, so you go through that process. and then you can start to influence around some of those regions as well. I guess this is an example as well where you've got what's the right approach, right? Depending on what area you might be interested in, you've got a small collar and you've got a fillet around this region. That adaptive sizing looks like it refines around that region and leaves these relatively coarse. However, what you might want to do is use something like a size control. You can use those defeature methods as well, right? So if you go to the body sizing, let's just add a body sizing. Sorry, go back to the meshing. We'll turn off adaptive. And if we go to the body sizing, we do have a defeature sizing, right? So if you've got elements that you want to defeature, right, like that small collar, you can specify that as well, right? And again, you can see there, based on the local elements, we can really start to play around with it. There are some additional things that we didn't really talk about. So we can specify things like the internal divisions around something. We can do things like mesh copy as well. So if you've got a mesh generated, we can copy them to separate faces and use them as a sweep method, and match control as well. So if we've got a periodic section, we can use this to map one face to the other and then sweep across or make sure that the two face elements are the same. Right. We've got some cyclical controls as well. We haven't talked about this too much, but if we've got surfaces, we do have some additional functionality to create welds between the two surfaces, depending on what you're trying to do. So you can see here, we've got a seam meld. We can also do things like a tent weld, and we can even apply, again, seam and tent. So we've got a couple of different options depending on what we try to do. It's not available in this particular model because I don't have any surface models, any surface elements, but you can right click and it'll be available for you depending on the geometry that's around. And then the other thing, so this is just an example, by the way, of why it's important to have a look at good quality, right? So you can see around this region, we've got some poor quality elements around here, and it's causing some problems with the actual stress. So we've got, really high stress concentration. By going in and starting to fix them up, you can start to see we've got more reasonable results around those regions. Now it becomes really important when we've got nonlinear problems, right? You can really start to cause some problems around this region. So again, we've got an example here where the mesh is really coarse. It's a bit too high around some of these regions as well. We'll have a talk a little bit about that a little bit later on as well. The other thing, I'll show you this as well. Generally, if you look at the help, the slides and lectures will be, by the way, I'll put all the slides and lectures up afterwards. If you do have a look at the Learning Hub, you go to the webinars, go to online training, you can download the previous FEA presentations that we've done before there. I'll make sure to upload them after next week because we've got the electronics sessions. But generally, again, we want to make sure we've got some good quality, right? And you can see here again the aspect ratios when they become very up to 20 can become very problematic. So we want to leave them as regular as possible. We've also got batch connections and beam connections as well. So this is an example where we might have surface geometries and we can use the batch connection model in order to connect all of it up, right? So this is an example about some examples about some submersibles. We've got a lot of shell geometry. The benefit is that it's considerably faster as well, and it will automatically bond all of the connections together to give you, a good high quality regular grid around some of these regions, right? So again, you'll notice, a lot when you've got a lot of these elements, it helps quite a bit. All right, so that is our kind of first session on meshing. We've got 2 hours left to go. Probably the next one will be on contact, and we'll talk about contact a little bit. So I've got a couple of case studies of some different components here, so different contact that you can see, and we'll have a bit of a chat about that as well. All right. So what I'd like to do though is I'm going to start over here in a little bit. Let's just take a 5-minute break. Let's just come back at around and make sure I get some water. We'll come back at 10. We'll come back at 10:15. We'll give it 10 minutes. We'll come back. We'll come back at around 10:10. We'll come back around 10:10 and start with some of the contacts. Going through the questions again. Yeah. So I'll be sending everyone. You can have a look at the CFD presentations in the webinars, right? And I'll add a link to that right now. So you can download the previous webinars and the previous presentations. And after next week, I'll upload our recent ones as well. You can see our slides there as well. And again, I'll put another link. So if anyone missed out from yesterday, thanks, Prasad. If anyone missed out from yesterday, again, the CFD material and the FEA material is up there as well. Right. All right, so we'll come back around in a couple of minutes, guys. Thanks. Hey, guys. All right. A couple of minutes over, but we should be fine. So some questions. Yeah, Mohsen will PDF slides. Have a look at the Learning Hub, right? Download the CFD and FEA presentations there. That will have the PDF slides. I'll make sure to update them probably next week. I'll obviously be updating them with the slides that I've done yesterday and today. And then I'll also ask Sam and Peter tomorrow to send me their updates as well and send along. A lot of the slides, by the way, guys, everything I've actually taken from here. This is actually from the Ansys training that is available on the, again, structural, getting started, the content, some of it's available kind of through there. If you go to the very top and have a look at the Ansys meshing, we've got some FEA lectures and content again inside there. And if you've got a specific topic, again, your linear analysis, your contact, all that stuff, all of that is, all of the downloads have the lectures links, have the lectures, as well as the actual tutorials as well. So, everything that I've got here, you guys will be able to find it. And again, like I said before, we're on support. So if you find that you're running through something and you've got something you can't quite find what I was showing you, feel free to reach out to us and say, hey, I'm after A, B, and C. You can just send them through, or send a link to where you can find them. All right. Cool. So contact. We're going to go through a couple of contact. The different types of contact that we've got available, right, inside Ansys. This one's going to be a little bit different. I'm just going to go through a couple of these slides just to give you guys a quick overview about it, and then I'll get into the model. Actually, I'll show you the model first. So all it is, and I recommend, by the way, if you ever try to understand something and it's not quite making sense, make a simple model. Figure it out, play around with it a little bit, make sure it runs relatively quickly, and you can dial in some of these settings. So I've just made a couple of beams here, right? Nothing special. I've made multiple ones, so I've changed the contact. The one at the top's bonded. We've got no separation, frictionless, rough, and then frictional as well with a 0.1. There's a lot of conditions and all this stuff around here. I'll talk about a couple of the key things that I reckon are relevant for people starting off. And then you want to have a look at the help just to pick up a little bit more detail as well, right? Got 4 different steps, fixed supports on the left-hand side, and I've just got displacements on the right. So I'm just moving components around, right? So if I play it, you'll notice what happens is that first it kind of moves out. I'll play it in a bit more scale up just to show you guys. So it moves out, moves up, moves down, then kind of moves back in, right? You can see how the different contacts really start to behave, right? So we've got bonded at the top. We've got, the second one, which is no separation. We've then got frictionless over here. So again, we're at the slide, there's frictional sliding. The rough here, right, it's able to come back, but because there's no sliding involved, when it comes back, it starts to arc. And we've got some frictional sliding, at the bottom as well, right? We can, again, look at stresses around some of these regions and identify what's happening. And we've also got things like contact tools as well, right? So we can pick up what the pressure on something might be, and what we might need to do, things like sliding distance as well, right? So what's happening though, right? What types of contact do we have, right? So contact generally used between two different bodies, and we've got a couple of different things that we can really specify. And really, when you're thinking about your problem as well, you really want to be thinking about, if I've got body-body interaction, how can I actually characterize it, right? Is it welded, right? Is it something like a bonded contact? So we've got no penetration, separation, no sliding between faces or edges. That's the other thing here, faces or edges. So is there contact between faces? Is there contact between edges? Do I have solid geometry? Do I have surface geometry, right? So these are things that you should be really thinking about. No separation, similar to bonded, except we've got frictionless sliding, right? The two at the top are considered linear contacts because we don't have a status change, right? Whereas the three at the bottom are non-linear contacts, right? So frictionless sliding, we've got no penetration allowed, but the surfaces are free to slide as well as separate without any resistance. On the rough, again, similar to frictionless, but there's no sliding whatsoever, right? And frictional allows for sliding, and there's resistance in that process due to the contact friction, the friction factor. And we've got separation as well. So again, you'll notice the bottom three were allowed to separate. So there's allowed to be a status change in the actual contact, whether something's in or out of contact. Whereas the ones at the top will always be in contact as well, right? So a couple of things we really want to be thinking about. So when it comes to things like the formulation, right? So how is this contact actually generated? So if I go to my frictional, you'll notice in my advanced options, again, we can play around with a lot of these things. We'll have a look at some of the advanced options here, right? So we've got different formulations, and these formulations really determine how these things will start to interact. Yeah, so Harshit, so yeah, the getting started material, if you go to the Learning Hub, right, best place to go, getting started, and you can see a lot of the getting started material here. Download the videos and the lectures and run through them. The lectures will also help you out as well. You can also, afterwards, you can rewatch a lot of these videos to give you a good general concept and then focus in on some of these things as well. Right. So the first formulation that we're going to look at is what's called pure penalty. So it is what's called, so it's a penalty-based method, and it's got this concept of a contact stiffness. And depending on the contact stiffness, there's also a certain amount of penetration as well, shown in the figure below. Ideally, contact is infinitely stiff and you've got zero penetration, but you can see here it causes us numerical problems as well. So that's why we want a little bit of penetration. Something that's negligible, right? Something that's small, right? If you've got a meter long and you've got something that's penetrating a millimeter, not the end of the world. If it's a millimeter subject though, and it's penetrating half a millimeter, that's something we really need to think about, right? So what happens is that, again, we've got a force applied, we've got this normal force coming in, we've got our stiffness, and we've got a certain amount of penetration. The normal, what we generally use though is what's called this augmented Lagrange. So this is again that penalty-based method, and it augments the pure penalty, right, with this Lagrangian term at the end. Because of that term in the end, it's less sensitive to changes with the contact stiffness, and it's generally the default option as well for whatever you're trying to do. Right. So again, this is the formulation. Let's just exit this. So this is the formulation here. So it's the actual, mathematics in the background, trying to determine when something comes into contact, depending on what type of contact, how is it actually interacting, what forces are being transmitted through it. Is there X amount of, penetration through a component as well, right? So the next thing I want to talk about is the actual detection method, right? So under here, we've got the detection method. We've got a couple of different methods here. Right, so the detection method again chooses location and shows you how things will actually get detected. So for the pure penalty and augmented Lagrange formulations, we've got what's called this Gauss point integration set by default, right? So you'll notice the program controlled, Gauss point set by default. And you'll notice on the left-hand side, what happens is that we've got these contact elements and these target elements, and these Gauss points, which are these X's, is where we're calculating what's happening, right? Where we've actually got contact. You'll notice, we've got what's called contact and target elements, by the way. So in red, we've got elements there, and in blue we've got elements. So the solver in the background almost puts like a skin on there of contact elements, and that is what helps determine how these two components are actually interacting, right? Depending on what you've got, so if you've got different formulations, there are other things like the nodal detection, normal from contact. So again, instead of looking at the Gauss points, it will look at the actual nodes and detect at what point does the contact surface, the one in red, actually come into contact with the target surface over there as well. When things start to become a little bit hairy, we can often use some other things like, again, nodal, normal from contact or to target. And instead of using these Gauss points, right, so if we've got like a sharp thing coming in contact with the target surface, you can see here, it will look at what the actual node elements are. So again, so the normal contact or normal target detects the direction of the forces applied by the interface there. Again, so there's some extra calculations in there, so it can get a little bit hairy when it comes to running the simulation. So this was, something that you might use when you're running it and you're having some problems with your contact. The other thing that we normally talk about and try to change is this normal stiffness factor, right? So again, going back to our electric garage, remember we've got some sort of contact stiffness. Now, again, like we said, ideally we've got something that's extremely stiff. We don't have any penetration whatsoever. However, that can be very difficult when it comes to convergence, right? There's a default value set as 10, but what we'll normally do if we're starting to have some problems is that we'll start to go in and start to change the stiffness factor and make it smaller, right? So if we make it smaller, 0.1 or 0.01, we will start to have a little bit more penetration, but it can drastically help when it comes to convergence as well, right? You'll notice here, so for bending dominated problems, we can have convergence problems, so reducing the value can help quite a bit. And yeah, we've got some things in there as well, right? Again, the other thing is I'll also play around with what's called the update stiffness, right? So again, coming back to here, we've got the detection method that we were previously looking at, so some of the contacts through there. We've got the normal stiffness. We can specify a factor. We can specify an absolute value as well, but I normally stick with the factors. And update stiffness as well, right? So what happens is that on each of the actual equilibrium equations, it'll start to update the stiffness matrix around some of these contact regions as well. And that can be really helpful when we start to have convergence difficulties in our actual simulation. Again, another thing with the contact stiffness, again, just emphasizing it's one of the most important parameters when it comes to accuracy and convergence as well. So just to reinforce that a large stiffness is more accurate, right? Less penetration, but can be difficult when it comes to convergence, right? So this is where having something that is a little bit reducing the stiffness can help when it comes to it as well, right? So we can have a look at that. Here's again just another example showing off the effect of that contact stiffness. It's one of the first things that I'll often go in and start to play around with. This is why I'm just emphasizing it. You'll notice when the contact stiffness starts to change, the deformation relatively similar, the equivalent stress relatively similar, but then we start to have a look at the maximum contact pressure, and that can start to change quite a bit when the normal stiffness reduces. And also, we've got more iterations in there as well. So max penetrations as well through that process. All right. The other thing I wanted to have a bit of a talk about was just introducing pinballs and some symmetric regions. So pinballs again is something that you'll see. It's like this detection region. If something is bonded, it will look within that detection region, that pinball region, to pick up elements. Right? If we've got something like a frictional where we can come out of contact, again, it's like a searching region. And if something's away from that pinball region, it's deemed to be opening or near as well, right? In the status. The other thing we want to talk about is the symmetric and the asymmetric behavior. So generally what's set is these is the auto symmetric behavior is set by default, right? What happens here is that the program evaluates the contact region and chooses which surface should be meshed with contact elements and which should be meshed with target elements. And this can sometimes cause some problems, right? Generally though, so if we look at the asymmetric behavior, in this particular case, the contact surface are constrained from penetrating the target surface, right? So we kind of go back to here, we've got the contact surface, it's constrained from penetrating the target surface. If we've got these two things flipped around, right, because the contact surface can't penetrate, we can start to have a little bit more penetration and it can cause some problems with our simulations as well. All right, so we have symmetric constraints as well. So again, in the behavior, we can set it as symmetric. So for the target and surfaces are constrained with both types of elements, right? So the program uses two separate contact pairs, a contact and a target element on both sides, right? So this is again, like this is generally something I don't play around with too much, but I wanted to show you guys what's happening here, right? So we've got a couple of things when we think about contact happening. We've got these, again, contact elements. We've got like a skin of contact elements, a skin of target elements. These things are coming into interaction depending on where our detection method is. So where is it actually being, where are we detecting that? We've got ways that we can change that if we start to having some problems. Depending on what we've got as well, we've got different formulations to capture that contact behavior. And one of the most important things is that contact stiffness, right? So how much the contact starts to penetrate. Ideally, we want something as stiff as possible, but that can cause us, big problems when it comes to convergence. So generally, we've got a little bit of contact stiffness, and we'll start to play around with those features. So like I was saying, so I've left these generally as default. I've personally found that a lot of the program controls are generally good enough to begin with picking up what it needs to and some of the formulation. So it's got a lot of smarts and best practices built into it. When we start to have problems though, that's when I'll really start to identify, a couple of these formulations or different components in here that will go in and start to really play around with and start to change, right? With this contact tool, by the way, it's automatically generated. You'll notice it's picking up all bodies and it's just looking within a specific tolerance. And what all I've done is gone in and changed the type on these separate components. Right. If you look at the contact tool as well, so if you right click on connections and you generate this contact tool, it just specifies, so let's just apply for, let's just add all of them. Let's do this again. We can generate the initial contact information. This is really important. For the model like this, it's relatively small. We know everything that's happening, right? But for very large models, it's important to have a look at your initial information. Sometimes what can happen, so it tells you what the contact side is, what the target side is, if we've got contacts that are active or inactive, and then how many elements that we've got contacting. Sometimes we might have things like penetration or a gap between some of these components as well. So if we've got a frictionless contact, something's coming into contact, we might have a gap, and we can see the resulting pinball as well. Now, you'll notice again, so we've got the gap. We can also right click and easily show what's happening around some of these regions. So the reason this information is important is sometimes, when you've got large geometries, the values might be very large, right? So instead of looking within a 2 millimeter radius, maybe it's looking in a larger one, right? I'm just going to force it to be bad. So I'm going to look for a 50 millimeter tolerance sizing. So it's looking, it's looking surface 50 millimeters. And again, straight away you'll pick up, because of that such a large component, even though these two things aren't interacting at all, it's picking up these two regions, right? So when you've got thousands of components and we've got customers that have this, it can be very difficult to pick up what's happening here. So if we delete this, we generate a new contact tool, right? You can see all of my contacts here. The default, by the way, you can see is bonded. Right, straight away you can have a look at the contact information. and we've got some problems, right? So you can see straight away if it's red, we've got things that are very open and they might meant to be closed. This applies for bonded and no separation contacts, right? So straight away it's telling us, all right, if we focus on this one, we've got a contact, it's bonded, it's far open, so that it's looking, remember, within that pinball region, and it can't find, the two faces at all. It's telling me straight away I've got zero number of elements in contact and I've got some problems. I can right click, go to the selection, and I can really start to hone in and figure out what's happening. I can potentially change something like this. If this is meant to be in contact, I can change it something to like a frictional, right? And let's just go in and regenerate that again. And we might start to see it change now, right? So now all of a sudden it's yellow instead, right? It's telling us that the status is simply open. And because it's a frictional contact, something might be coming into contact later on that might be acceptable, right? But generally what you want to do always, have a look at your yellows and your oranges. So again, you'll notice orange is telling you that something's closed, but you've got large amounts of gap or penetration, right? And you want to have a look at things like the pinball, right? And again, you want to identify, click on them, right click, go to the selected icon. You'll be able to pick up straight away, on the left-hand side, the formulations, what's happening there. You can visibly see what's happening. And on the right, at the top here, you've got these views, right? So you can sync the views up and you can visibly see what the, elements are and how they're playing around, right? So let's go back. I'm going to change this back to something like a 0.1. Let's create on contact. It's good to go. The other thing that's important with this as well, so we'll have a look at that, this real constant. So these real constants will give us information if something start to go wrong in the actual solver. I'll just walk through this process, right? So all I've done is set up a basic mesh, nothing special. I made these name selections to make it easier for myself, right? So what I did, instead of me selecting each of these individual faces, you can select a face, right click, generate a name selection, right? And what I want to do is select geometry which has the same X location, right? So we'll just call this selection 1, press OK, and you'll pick up straight away it creates what's called this worksheet, and we've got, and it's telling us what it's doing, right? So it's adding faces with a location that's equal to a specific value, and it's found it's been able to pick up all of these different faces. The benefit of that is that I can scope a fixed support to a name selection from there, right? So it makes it super easy. The next thing that I've got here, I've got multiple steps, right? So if we look at the first step, the first thing that's happening is that I'm just moving the block to the right 1 millimeter. The step afterwards, I'm moving it up in the Y by 1 millimeter. I'm then moving it back down, and then I'm moving it back in, right? So in my analysis settings here, I've got 4 steps that I've specified, and I've also got what's called substeps. We'll talk about substeps a little bit later on, right? One of the things I'll note, by the way, is that sometimes it can get pretty intimidating because there are a lot of settings that you can go in and really start to change. And I know I personally struggled with this as well, understanding, what buttons we can really play around with. What I always recommend, especially with people starting off, the program defaults are generally great when it comes to finding the most robust formulation possible. So leave things as default. Sometimes when you're solving it, you'll get warnings and informations about what you should be doing, right? So have a look at them and then you can start to make some changes. But the key thing is that before you actually make any changes, have a look at the help, have a solid understanding about what's actually doing, what does say weak springs mean, how is it actually being applied before switching anything on? Because the problem with FEA is that it's very easy to get a result. The problem is knowing if that result is appropriate, if the assumptions, the boundary conditions, the formulations used are appropriate, can be a bit difficult, right? So it takes a bit of trial and error, right? So let's just, I'm going to solve this. As it's solving, I've inserted what's called this deformation plotter, this tracker. So as I've got components that are being updated, I should be able to temporarily see some of the results as well. All right. It's solved pretty quick, but one of the things you'll notice is if I have a look at the solution information, we'll just give it a second. So it's writing out files in the background. If we have a look at the solution information, we'll give it a sec. All right. We can look at some of the convergence plots as well. So the solution output, by the way, so always good to have a read through this. It takes a while to kind of understand a little bit about what's happening. Sorry, question coming in. Create a motion in different directions for components. Yeah, mostly. So I'll show you how I use the displacement to create motion in different ways. So the solver output, you notice kind of what's happening. These key options are all about what's happening on the elements. So you can see here we're using what's called a solid 185 elements, and these key options simply tell the solver how is it solving and what's happening in the background. We've got some information about some of the contacts that have been generated as well, right? So whether things are symmetrical or they're deforming. If we scroll down a little bit, so we've got these. You can see here we've got solid elements, we've got contact and target elements as well. So remember, there's like a skin of elements on top of the actual, the visible mesh that you can see, and these elements transfer the contact, right? Transfer loads from one to the other, and then depending on if it's bonded, frictionless, frictional, the load transfer is different, right? Do we get just direct transfer or do we get some shear as well? We've got some equilibrium equations, right, that are being solved. And we can keep on going, right? One of the things that we'll pick up in a second, so we've got a couple of different models as well. I'll try to find them, maybe try to find what's called real constants. So one of the things I wanted to show you guys, sorry, was, here you go. So the real constants here, these real constants, what they're talking about, so constant 12 and 11, are the frictionless contacts and the contacts that are generated for us, right? So sometimes when we start to have problems, it'll say, real constant 11, too much penetration, go back and fix it. You go to your information, you look at what real constant 11 is, go to the tree, inspect it, and you might need to go in and make some changes with that as well, right? So it gives you a bit of information, and at the bottom just tells you what's happening. We've got these force convergence plots. So we're not just simply applying the load, we're applying a fraction of the load. We're looking at what the convergence is, comparing it to the criteria. And if it meets those conditions, we've got a green tick. And you can see after a while, we've got some blue sub-steps as well, right? So again, those sub-steps are the different steps that are implemented. And in each one of these steps, a different thing is happening to that block, right? So let's just focus on the block here for a second. We can insert deformation just on that block, right? So I can hit the play button and it'll go through that process, right? You'll also notice straight away I've got a bunch of these dots. So each of these dots is one of those steps, right? Those equilibrium steps, right? Because remember, I'm not applying the full load. I'm applying a small section, looking at the stress results. I'm applying another section, looking at the stress results, and then applying all the way, building it all the way up. I can select, by the way, a specific thing and retrieve that specific result, right? Or I can use the actual tabulated value on the right as well. So I can go to that, retrieve the result from there, right? So again, if we kind of zoom out, you'll notice what's happening. It's moving up, down, moving back in, right? At the top here, it's scaled up quite a bit. So let's just drop it back down. So notice a bit of, and then we can look at it, right? So let's just say from there to there, we want to play what's happening. It's sliding, coming up, right? So that's exactly what we expected. And then on the down, so it's coming into contact and then sliding back, right? So, I mean, this is performing exactly as we expected. Let's also have a look at things like the stress on that particular component, right? So again, we can chart it and you can see what's happening, right? So I'm not caring too much about the minimum or the average. I just want to care about what's happening with the max. So you'll notice for the very first time, there's just a bit of sliding, but it doesn't really look like there's too much stress in there at all, right? I mean, what's the maximum over? So we can look at the maximum, you know, e to the negative 14. Not much is really happening there, right? Even for the second step, right? So we're just simply coming off. So it looks like it's sticking a little bit and kind of coming off, right? Now stress starts to increase as we start to impact, right? And we start to make some impact with that surface. So again, we'll see it goes from 0 all the way up, right? So we can again track what's happening, right? And I can look at that specific value, go to the maximum, right? This is what the stress is. And then we can start to see, you know, in that particular component, because we've got the whole thing stressed, you know, the stress values are relatively large and it's kind of sliding in. All right. I can also look at the contact tool, look at the post contact tool. If we just focus on that frictional component, we can evaluate the results. Again, we can look at what's happening, right? So that first couple, we can look at the status, right? So it's looking at that pinball region. Is it far? Is it close? Is it, you know, what's happening with it? You notice towards the end, it's just sticking and it's sliding, right? We can look at what's called the sliding distance as well. So, right, so we can again go in and start to really inspect what's happening around this region. Right, and you can look at things like the pressure as well, right? So what pressure is really being applied on that interface, on that contact, right? So hopefully that gives you a good idea about what you can do there. So, you know, afterwards, what I did is just I ran them all, right? So looking at them one by one, we've got a bonded contact at the top. Because it's bonded, everything's almost like it's welded together. So we don't have any separation here whatsoever, right? Over here, we've got the no separation. So when it lifts up, it doesn't allow it to separate. So the bottom lifts up with it, but it's able to kind of slide in and out, no problems whatsoever, right? I think we've got a frictionless here, right? So it's able to move. There's no shear forces whatsoever. It just moves across, moves up and down. As it comes back down into contact, right? We've got contact that's established and it's able to slide back. Now the rough constraint here. So initially there's sliding, right? It's not really making that much contact, but when it comes into place and there's a bit of pressure, we can see here, we can start to see what's happening here, right? Halfway through, or if we just look at the end, it looks like the elements right on the far end it doesn't allow any sliding whatsoever, but with that happening, all of a sudden we've got the elements locally around here bowing out as well, right? So you can see the true scale. So that's, you know, that's the type of contact we can expect. And then again on that we can see similar to the frictionless, it's coming in and out. Now the biggest difference though is if we have a look at, say, the frictional and rough. Let's have a look at the status. So you can see here the pressure on a couple of those elements are very large. All right, so let's get rid of the rough. And again, through here now we can see what the pressure is when it comes, right, when it's out and it's coming into contact with my second plate, and the pressure is still relatively large as we've got some sliding. And we'll notice as well, so we've got frictional stresses. We can also have a look at penetration status as well. We'll notice straight away that we only really have any frictional stresses on the component on the right at the very bottom, because we've got frictionless sliding at the top. And if we look at everything else, we'll reevaluate everything. And you'll notice again, so we've just got, so it looks like we've got some frictional stresses on the rough, right? It's very large, but predominantly it's all sorry, we've got bonnet in the bonnet as well, but you can see that the values are very large. I mean, if we start to get values like this, we probably want to have a look back at our actual simulation as well and review our results. Cool. So hopefully that gives everyone a good idea about the different contacts that are available with inside mechanical. So just a quick study to show you, so we've talked about what's actually happening on the contact level, things like the different contacts that are available and the formulation. So what mats is actually used to detect contact and detect force transfer between them. We've got different detection methods as well, depending on what's coming into contact. And we've got some things that we can reuse as well, right? Things like the contact stiffness, if we start to have some problems with our actual simulation, and also things like the behavior as well, right? So what's really coming into contact with with the other component, right? The other thing, so we didn't talk about in too much detail. So we do have joints as well, right? So this model isn't really particular to joints, but I'll show you how to create a joint. So if we go to connections, right click, we can just generate a joint here. Depending on time, I'll try to have a look at, I'll show you guys a little bit more about the joints. I still want to get through the linear analysis and set up a couple of conditions. So you can see here the type, we've got different conditions as well. So if you select a revolute joint, we've got options for stiffness and dampening. And generally what you want to do, you want to specify a component here, and let's just say between that as well. And it will, based on the RZ, start to revolve around that specific area, right? If you want to go in this particular case, we probably want to go in and make some changes to the actual coordinate system, because we want it to revolve, say, around the Z coordinate system, right? So one in blue. And we can start to make some changes around there, right? So we can have connections from body to body or body to ground, right? So we can have that, revolve. We can have this revolve from this point in the actual geometry as well, if we wanted to set it up that way. And that comes down to, I guess, understanding what your actual condition is, what's the geometry and the material around there, and how does it actually interact with as well. Right. The other thing that we can do is that we can insert additional things like springs, bearings, and beams. So if we've got something like a spring, right, we can have a spring between two geometries. So let's generate a spring between the top there and the bottom. Right, and then in that spring, you'll notice it'll put some spring elements. It'll put a spring element visually to show you. And we can then specify things like the spring stiffness as well. We can go in and start to make some changes to some of the conditions. So where is it scoped to? Again, we can scope it to the ground if we wanted to, and the reference and the mobile conditions as well. So the reference and the mobile, again, similar. We've got just two faces. You can see the reference is in red and the mobile is in blue. And if we go to the connections, we can also specify things like beams, right? So if we have a bunch of bolts and we don't really actually want to explicitly model the bolt behavior, we can give it the radius, and then we can pick between, you probably pick between two holes, right? Something like that. We can put, a beam connecting the two of these things together. And then again, we'll transfer load from one to the other, right? All right, so we talked about kind of the different connections that we've got. I wanted to focus on contact just because this is what most people do. If you do have, joints and things like that, I'll try to look over it towards the end, but I encourage you to go to the Learning Hub, again, go to the contacts and connections, and have a look and run through some of the training material that's around there. If you run through it and you want a little bit more help, again, feel free to kind of reach out to us on support. All right, so another question, Mohsen, can we duplicate the pattern motion for two components? So Mohsen, maybe we'll talk about that in a little bit with the boundary conditions, right? So as an example, what I've done for this particular case, I've got a displacement boundary condition. So I've got different boundary conditions here that I can play around with. Again, similarly at the top, I've got, my loads, forces, moments, pressures, if I've got bearing, things like bolt pretension as well. And I've got supports as well, right? So one of the supports that I use is this displacement boundary condition. And in this displacement boundary condition, I can specify a certain amount of displacement, right, in the X, Y, Z locations. And what I've done is I remember created this name selection on all of these faces here, right, on the right-hand side. And I'm able to move them all in kind of lockstep, right? So depending on exactly what you're trying to do, that's one of the ways that you can kind of duplicate motion between two components. Obviously, you'll have to, depending on what your project is, characterize what that motion is, right? If it's cylindrical, right, you might need to change the coordinate systems. If it's moving in an interesting pattern, again, you might need to decompose it into X, Y, Z locations, or it might be appropriate to maybe have it, have a joint and the joint simply follows a curve or something like that, right? So there are different ways depending on exactly what you're trying to get out of it and what motion that you're experiencing. So another one from Jimmy. When you're using beam elements for the bolts, is there a way to get around stress concentrations? You get around the circles and edges. Yes. So what Jimmy is referring to, so I can make a, let's just make a quick study just to show you. I might as well make it. Yeah, I'll make something quick just to show you guys what's happening with it. And then I'll answer that question as well. So while that's going, motion spring. Is the spring has bending deformation or is it linear movement? It's just linear movement, right? So it's a linear spring. You can specify like a non-linear spring, give it different stiffness values. There are some elements in there as well that can just have tension only springs as well, depending on what you're after. But this is just a, you know, a 1D kind of element, right? So if you've got a non-linear spring in bending, you might want to reconsider using that element and use something else, right? So let's just make this 50 by 50. Let's go back to 50 by 50. And let's just chuck a second in the middle of around 20. And we'll come 5, right? What we'll do, so Jimmy, instead of selecting the edge, right? So let's just make, I'll make a second component. But what I'll do, I'll take this and I will copy the edge out, you know, say if you have 5 millimeters. So this might be maybe the bolt, right? Where the washer head might be, right? Let's just say we take that component and we move it down, you know, 15 millimeters, right? Let's say we normally got a bolt between these two components. What I definitely might want to do is take that, and if I double click that, it's just going to flip it 90 degrees. So that way I'm going to select and control both of these two components and bring them together. Right, so let's go back to here and we'll set up the model. So we've taken another hour, by the way, to do contact. So we'll take after I show you this, guys, unless you have any questions, we'll maybe now take another 10-minute break and come back and do the linear analysis. You can... All right, so I've got these bodies here. Whoops, I didn't have any boundary conditions. That's fine. What I'll do, so in my connections, I'll right click, insert a connection, and I'll specify a beam, right? I'll scope from this face at the top here to this face at the bottom, right? And actually what we might do, similar to before, let's just to illustrate what's happening, just in case people don't understand why we're going to be doing it this way. I'll just make 2 of them. All right, let's just clear that. And what radius do we have here? So if I select that radius 10 millimeters, awesome. So let's put that in. So we've got a 10 millimeter component there. And it's going face to face. Now in this, I'll make another connection where, again, I've given it a beam, 10 millimeters, and instead of the face, I will simply select the edge. So I'll just go edge to edge. Right, so that's good. I'll just generate the mesh, not too fast. Now, when it comes to boundary conditions, so let's just give it a, let's just fix all these faces here, right? And we'll do, whoops. Actually, we'll just fix the top. That's probably just going to be easier. And we will just pull this down by a, instead of, so I used displacement before, right? So I can pull it down by -1 millimeter. Just to make it a little bit different, what I'll do, I will specify a force instead. So I'll use this as a force. Instead of vector, I'll give it a direction, so a component, and I'm just going to give it a unit load, and actually we'll give it 100. And we will hit solve. Materials, so I forgot to assign some materials here. F5 is a keyboard shortcut to solve quickly. Right. So what we're doing as well, by the way, is instead of explicitly modeling the bolt and the complexity and the geometry and adding all those features, we're just modeling the bolt as this beam element, and we've got load that's transferred through the beam element, right? So again, having a look at our deformations. So we've got, if we extrude it out, so we've got some similar deformations, right? Got a lot more over here. But notice we're fixing the face on the left to the face there, whereas we've got edge to edge, right? And if we have a look at the stresses, right, we'll have a look at the bottom elements. Right click, insert stress, equivalent stress. So instead of doing that, what I'll do, I'll show you the other way. So at the top here, we've got the menu. Look at stresses, we can go equivalent. All bodies instead, we'll just select the two of them and it will apply on that one and we'll evaluate the results. And you can see straight away, right, what Jimmy was mentioning is that we've got these, we've got stress concentrations because we're attaching this to the edge, whereas on the left-hand side, we've got significantly reduced stresses because we're distributing that force around that face, right? If you go to the solution information and select geometry, you'll see, by the way, what the constraint equations are. So you can see there are equations that are being constrained to that the tip there, and we've got around there as well. What actually we might want to do, so the reason we've got these weird spiders is that we've got some nodes here that are sharing between the constraint, the beam, and the boundary condition, right? So what we might do, we might go in and just make some changes to the boundary condition. Run that again quickly, just to make sure we've got some constraints that make sense. I guess that's another thing as well. When you're doing these constraints, you just want to make sure you really think about how you're constraining the nodes and elements around here. If we've got overlapping constraints, it can sometimes become a problem. So now you notice, right, all it's doing, it's taking all those faces, you know, it's coming out, constraining the outside face to the middle, right? Same as over here. Whereas on the right-hand side, it's just taking those edges. And when we have a look at the results again, you'll notice, you know, because it's just constrained to the edges, we've got some stress concentrations around there compared to what we've done on the left. So, so that's what we can do, right? So hopefully, Jimmy, that answers your question. Yes, we use SpaceClaim for that. Is there a tool such as a spring and Ansys able to provide linear and bending deformation? Merson, I don't think there's a simple 1D tool that allow you to do that. If you've got a problem where you've got a project that, you know, you've got a spring that is bending and deforming in more than one axis, it might be a situation where you want to actually model that spring. If you've got a particular project in mind, by the way, just send us a message on support, mate. We'll help you out. Stefan, can you change the geometry in SpaceClaim without altering selections in structural? So this is actually a relatively new feature. If you make changes in SpaceClaim, you can go, you know, right click update and it'll come through. In the latest version, so 2021 R1, you can right click on geometry and you can freeze the mesh. So it just kind of freezes what you've done, right? So two geometries, get rid of the mesh. So the two geometries, I've frozen the one on the left and the one on the right is free to move. If I go in here and let's just say we make some changes and make both of them larger. I'm testing this on the fly, so let's hope it doesn't break or I haven't forgotten to do something. What we should see happen, oh no, we've got both of these two things that changed, right? So, okay, even though the body's changed, the mesh stays exactly the same. You can see the mesh changes on the right as well, right? So, so you can see that you can use this mesh, so it freezes the actual mesh given on that component, right? So that's if you wanted to fix whatever meshing constraint or something like that, or geometry you've created and just compare between the two of them. That's one of the ways that you can do it. If that helps, Stefan. Thanks, Jimmy. Thanks, Merson. Yep, all good, guys. All right, so that's what we wanted to. What's what I wanted to cover today for the contact side of things. I feel like we've covered quite a bit. Yeah, so we've gone over again. So we've gone over formulations, detection methods, what's happening in the background. We've then created a small component where we've got all the different contacts that are available, and we were able to have a look and how they all perform and how they deform and how they're different. I've just showed you guys how to specify things like additional things like joints, beams, and springs. And then we've set up a quick analysis where we've just done some two beams as if we were modeling a bolt, and different ways that we can model it to see what's happening there as well. All right. So no more questions in the chat. What we will do is we'll probably give it another 10 minutes. So we'll come back at around 10:10. And we will get into the linear structural side of things, right? So let's go back at 11:10. Sorry. Hey there, everyone. Hope everyone's back. Everyone's able to go out, maybe get a coffee and come back. So, all right. What we'll do, I'll go over a couple of key things, right? So, yeah, we're going to be sticking a little bit more to the application side of things, right? So we're not going to go too deep into the actual maths behind it, but we've talked about this before. What we're trying to solve, we've got this stiffness matrix K, we've got displacements X, and we've got applied some sort of force, and we're looking to solve the actual displacements on the nodes. And then from there, from the nodes, we look at the integration points to determine the strains as well as the stresses, and that's what we can see on our actual system. All right. So we've talked about, well, I've actually talked about this. So most of the geometries that we've been playing around with are all flexible geometries, so we can look at stress and strain on them. We can specify things as rigid as well. So it'll generate surface elements where we've got things like contact, and then everywhere else it won't actually determine things like stresses internally on our actual object as well, right? We've talked about contact and setting up our different types of contacts, and we've had a little bit of a chat about some of the analysis settings, and we'll go into that in a little bit more detail as well. So first I want to go over some of the different loads and boundary conditions that we've got available to us, and then we can and then we'll go in and actually look at a couple of examples, right? Just a couple of cases that we've got here, right? So when we think about loads and boundary conditions, generally what we're thinking about is how are we actually loading the component, right? Depending on what we've got. If we've got solid geometries, we're thinking about degrees of freedom in the XYZs. And again, if we've got shells and beams, we need to also be thinking about degrees of freedom in the rotational axes as well, right? So if you've been given a project, again, try to think to yourself, all right, how am I going to break this down? Do I want to give it a force? Do I want to give it a displacement? What are my degrees of freedom? What is constrained? What can't move, and what am I allowed to move as well? Right. So when it comes to, so we've already looked at actually applying some loads. So we can apply things like a force in either a vector or through components. And we can also play around with things like the coordinate systems as well, depending on what we're after. We've got some things like boundary conditions like acceleration, gravity, and rotations as well. So if we fire up one of these components, you'll notice if you go to static structural, get our environments. We've got all these ones. We've got our loads, boundary conditions at the top. And if we look at our inertial, we've got, again, our accelerations, standard earth gravity, rotational velocities as well. So we can specify, again, resulting forces. So for acceleration, you can see the units, length over time squared. We can give it as a vector. And just as a note, if we've got something coming down, the resultant force will be coming up. Earth gravity is a little bit different. If we've got the Earth going down, resultant force is going down with it. Right. We can also specify things like pressure. Right. So again, force over area, we can give it in different components. It can be positive or negative. We can specify things on lines and on edges as well, but generally we just want to be wary of stress concentrations. Similar to forces, again, we can apply them on points, lines, faces as well. You'll be able to note what the units are in each of these systems, and we can specify components. We can even specify moments. A couple other things, right? So if we've got hydrostatic pressure, so if we've got maybe water within a container, and we want to specify things like the fluid density, we want to capture what the hydrostatic pressure might be, we can definitely do that as well. We've got some additional loading conditions, some specialized kind of forces, things like bearing forces. So you'll notice on the left-hand side, we've got bearing forces and we've just got a force applied to it. And the difference is, you can see on the right, the actual distribution on a bearing load is different. We're not uniformly applying pressure or a force on a face. We've got a lot more at the very top of the thing, similar to what a bearing load might be. We can apply things like remote forces as well. So we can actually pick a point of origin that we want to apply the load from, and it could be far away from where we're applying it on the face. And that could implement, that represents, might be there's a component out there or where the load might be coming from, and we may not necessarily be modeling that component. So we can still model the force, but we're also now modeling the moment that can be created from there, if there are other secondary effects from that, right? So we can use remote forces and again specify our XYZ locations. We had a model before, but we can maybe open up and talk a little bit about bolt pretension as well. So again, you can see on the example on the bottom right, we've got an example here where we've got a bolt. Generally, we're going to apply some sort of pretension, some sort of force, and then we're going to see how the structure actually deforms. On the right, we're actually, we've actually CAD'd a bolt. We can see the 3D complex stresses going through the bolt shank, the head, as well as the washers, and the nut at the bottom, or similar to what we had it here before. Right, we can just we can measure it as if it was just a beam, connecting the top and the bottom. Right, we're not going to get any complex forces or stress distributions or singularities performed because of the geometry at the top, but those are the types of simplifications that we generate as well. Right. Now we're looking at, we can do thermal analysis as well, so we can apply thermal to a body, right? If we wanted to do, so that's a pretty general load, but if we wanted to, we can add things like a steady state thermal condition where we've got a lot more thermal boundary conditions, right? So in this particular case, again, we've just got temperature, but we can even apply things like convection, radiation, we can give it heat flux as well. So depending on your boundary conditions, you might want to think about what analysis systems do I need, right? Is it and if we've got more than one analysis system, so if it's a thermal analysis system, the other question you need to ask yourself, how tightly coupled is the physics? Can I run the thermal analysis and then look at my results? Or will the thermal analysis, deform the subject so much such that we need to account for the static structure, the structural results as well? And in that particular case, we've got what's called a couple field element, where we can solve both. Problems together, right? So I've got a question here. What's the recommended connection between a bolt and a nut? Bonded frictional or high friction constant. So if you've got a bolt and a nut, you probably want to leave something like that as bonded, right? So we didn't talk about it too much, but you want to think about, even though everything has friction, the question you really want to ask yourself is, in this particular environment or whatever's happening, are you going to see sliding? Are you going to see things moving around, right? Because you can leave things as frictional, but like I was saying, the frictional coefficient, the frictional is a nonlinear contact, so it means you're going to have more iterations. If you could have something as bonded, it means that we're going to be able to solve a lot quicker with a lot less problems, right? So for something like a nut and a bolt, if you're not expecting things to move at all, I just leave it as bonded. If you're expecting things to move around and you reckon there might be some problems, maybe frictional might be appropriate. But then you also want to be thinking about how are you modeling the thread as well, right? So you want to think about that stuff. And again, these are particular to your particular problem, right? So if you depending on what you're interested in, so it always comes down to what is your main area of concern, right? If it's around specifically how the bolt and nut interact, then you want to model the threads and all that. But if it's just a small part and you just want to make sure load gets transferred from component A to component B, you can make some simplifications, right? So that's what we want to think about the loads. Now, when it comes to our supports, right? So it can be a bit difficult. So I sometimes just have a lot of these things saved out, or I have a look through the help, because we do have quite a bit of loads and boundary conditions that we can apply. So if we've got a fixed support, so if we've got solid bodies, we're just constraining degrees of freedom in the XYZ, and again, surface bodies and rotations, we're constraining the rotations as well. Again, displacements, like I was showing you before, so I can manually constrain specific degrees of freedom. I can also enforce it as well, right? So I can enforce, like you guys saw before, a 1 millimeter displacement, right? So we got things like elastic supports as well. So it applies what's called a flexible kind of frictionless support to it. And we've got at the bottom here a foundation stiffness. So as an example, that can be used for things like soil, right? Where maybe something is resting on soil, the soil has some sort of stiffness, so it's not a perfectly stiff product. And you can model that type of analysis. Frictionless supports, this is something I use quite a bit. So if it's a planar surface on the left-hand side, so you'll notice it's free to translate in the actual plane, but it can't translate out of the actual plane as well. So symmetry, if we had a symmetric condition, so if I was to cut this in half, I'd be using frictionless supports quite a bit, right? Because it allows the part to move again in and out of the plane. Sorry, it allows the part to move within the plane, but not out of the plane, right? So I hope that helps you out a little bit. And on the right-hand side, you can see, so the tangential and the axial directions are free, so it's allowed to kind of rotate and move up and down, but it's not allowed to grow in the radial condition as well, right? So depending on what you're attaching it to, we've got some different types of constraints, right? We've also got cylindrical. So let's say you've got a bolt and you don't actually want to model that bolt, but you want to model the effect of it, right? You can actually apply a cylindrical support on the face, and then you can again manually fix the radial, the axial, and the tangential degrees of freedom as well, right? So this is again comes down to, before you open it, you want to think about what are your boundary conditions, what can you simplify, what can you get rid of. If you've got something that's constrained, you can use something like this to get rid of bolts and get rid of the complexity within the model as well. We've also got things like compression only support. So again, it applies constraints in compressive only field, right? So you can see again on the left-hand side, we've got two examples here. When we've got surface bodies, instead of a frictionless, what we want to do is that we also want to think about rotation. So we've got the simply supported here. So it prevents translations, but all rotations are free. If we've got a symmetrical, if we've got a symmetrical boundary condition, we also want to be thinking about fixing the rotations as well, right? And again, so these are all assumptions, and these are all simplifications that you can make to the model, which allows you to make the model, run quicker as well, right? Now, we talked about contacts and supports as well. So the difference, though, is we've got contacts, which is defined as the interaction between two bodies, whereas supports are a interaction with the body to the environment, right? So on the left-hand side, maybe we've got contacts to specify things like the frictionless supports, and on the right, maybe the component over here might be fixed, right? So we want to give it supports on the left, where the left-hand side is attached to the environment, and then contacts on the right, where we've got bolts that might be frictionless, or components that might be frictional as well, right? So having a look at something, so let's just fire up another example. So I've got a couple of test cases just to show you guys some different things here and there. All right, so I will do, let's just bring it in. So let's bring in this is one of the examples from the training. Right, so I'll be actually walking through this one here, mechanical basics, right? So this is the cap fillet. We'll apply some loads on the outside. We'll then start to look at some of the materials. We'll have a look at that later, and apply some boundary conditions as well, depending on what we want to do. All right, so we've got this cap fillets that's come in. I'm just going to generate the mesh, and we'll leave it as is. Mesh isn't amazing, but it's not what we want to focus on right at the moment. So first I might think about the load. So in this particular case, we're going to apply a pressure on the outside, right? Because we've got some radiuses around there, if I double click on that, it will extend it to the limits, right? So we see it extends it up until you get a 90-degree impasse, right? So we can do that, and I can right click on static structural. You'll notice, the top are all my inertial loads. We've got my forces, we've got my supports, and then at the bottom, we've got some additional things as well, right? We've got interfaces, contact sizings, and things like that. All right, on the outside, we're going to apply a pressure, and let's just give it roughly a 1 megapascal pressure, right? If I forget to, by the way, apply some boundary conditions and I just hit the solve button, I will get a thing straight away saying, you can have a look at the message saying we've got some pivoting controls, right? So there's not enough constraints. We've got some sort of rigid body motion. We should have a look. And again, it'll tell us, a similar thing. It'll constrive matrix, and it'll also tell us sometimes what nodes are causing some problems, right? So if I go to the solution, again, I can also view that information in a little bit more detail through here, right? So if I scroll up a bit, so you can see here again, we've got an error. We've got some pivoting problems, and if it's a specific node, we can actually use the filter, right? So we can go node 2471, go to the geometry, right click, select mesh by ID. I want to look at the node, put that in, and I can select that specific node, right? So, that's the first node that's just causing some problems. But we know in this particular case, we haven't actually constrained our problem properly, right? So what we will do, however, is let's just say we've got a bolt, something like that, right? We can select these components in here, and we can give it a cylindrical support. What we'll do, we'll fix it. So it's fixed in the radial, fixed in the axial, and it's also fixed in the tangential as well. So it's not going to be able to move around. And if you're unsure, you can always go right click. We'll do a quick solve of it, and we'll have a look if we've got the correct boundary conditions, right, to stop it from moving around. Right, so notice we've gone through a little bit more and we're starting to get to a good solve, right? Right, so we've got some sort of result. Now on the results, again, we've got a ribbon bar toolbar at the top, but I can right click and look at things like my deformation as well as my stress, and I can evaluate those results, right? So I can have a look at what's happening. Again, so in this particular case, I've just like held it at the bolt holes. I'm applying some sort of pressure. I can animate that. All right, you'll see at the top, by the way, my results, I'm scaling it up by 71. I can leave it as if it's a true scale, right? And if I do that, it doesn't look like there's a lot of movement there. So we use this scaling just to emphasize what's happening, right? We can also look at things like our stress and identify where we might have some stress concentrations around some of these regions as well. That stress is very large for what we've got. Right, we can then also go in and say focus on specific areas, right? So let's just say maybe we've got we've been asked to maybe have a look at maybe some of these ribs, right? So we can use our face selection. We can pick say a rib up, right? And we can insert stress on that specific face there, right? So now we can have a look at that in a little bit more detail and understand, okay, do we need to go in and make some changes? You can clearly see we've got some stress concentrations at the top here around some of these regions. So we might want to go in and start to make some changes as well, right? So in this particular case, what we can do, so let's just focus on a specific area. So let's focus around this region. One of the things that we can do is, let's just put some stress on there. Right. At the moment, by the way, we're looking at the nodal averaged parts as well. We can have a look at the unaveraged conditions as well. Right. So this is what's happening at the integration points. What happens normally, it comes to the integration points and it averages across that element. So we can look at what's happening. We can also look at things like the nodal difference as well. So if there's a large difference between some of those components, we've got pretty large stress differences around here. And this is, again, another way that we can identify, if we need to go in and make some changes, right? But generally, I mean, when I look at this, I look at it and I try to make sure. So on the left, we've got a couple of axes here. Each one of these things is roughly a 10%. So I try to make sure we only have like one color band across the actual element, right? So let's just say we go in, we want to select these regions and we want to insert some sort of sizing, right? Maybe bringing this up, we want a sizing of say 0.5. Let's generate a mesh and let's see what happens locally around there, right? So it's a little bit smaller. Maybe we should make this a little bit smaller. Right, and what I might do, I might add both of these faces here as well. Right, so the more mesh elements you got, the longer it is going to take to run, but the better we can actually capture the stresses around that region locally. Now, you'll notice, by the way, straight away there's a pretty large transition. So in reality, I probably want to go back and either make some changes, make the mesh locally around here finer. I can use things like a body of sphere of influence if I wanted to as well. Right, previously, the stress around there was around 500. And we can have a look at the stresses. So as it's solving, got a question, can we output axial shear forces and moments instead of stresses? So what we could do, so if you want to go stresses, there are some other conditions here. So you can look at things like the principal, maximum, the shear as well. So yes, these are different components that you want. If you want to output it in a specific, say, coordinate system, what you would probably want to do, if you were to select that face, there are some components where we can actually specify. I mean, a coordinate system for axial wouldn't make too much sense here. But if we go to the total deformation, we can, if we select something like an edge, we can. What do we want to do here? We can specify that though around some of these. Actually, if we select that, make it total deformation, we can enforce what's called a path. We can convert it to a path result, right? And it creates a path around there. We can evaluate it. We can get a graph out of it. But one of the things that we can do in the path result is, so there's a way, I can't remember how to get into it now, but there's a way we can change the coordinate system such that instead of a global coordinate system, it follows a cylindrical coordinate system. That way we can pick up that specific region, right? So let's do that. Make it cylindrical. Does it allow me to do that now? Go down. If I convert that one to a path. Can't do it at the moment, but I'll you can have a look later, and there are ways that we can output these things in different coordinate systems if we need to. Right. So going back to this problem though, looking at what's happening around here. Now we've got a bit of a better, stress gradient across there, right? We've got a couple more elements to pick up what's happening. Still probably want to go back and then make some additional changes, maybe change this to make it a little bit smaller, just to pick up better stress around that region, right? Again, if we go to say things like the averaged, we can have a look at it. So now again, we've got some better distributions. If we look at the nodal difference, right, we've got relatively small differences around that region as well, right? Again, around here, you can see the difference can get quite a lot larger, and I think we've got some regions around here that are quite a bit. Right. Look at actually where the max is. There you go. So we've got this region around here where we've got the max nodal difference between the nodes that are connected around there. Right. Okay. So we've got those things. Go. All right. So I mean that's how we can kind of set up some basic conditions. And how we can set up that type of analysis as well. One of the things that we probably want to look at is the materials, right? So I've just been leaving it as the standard materials, right, which is just structural steel. If you look at the materials there, you will see a little bit of data about it. So this is coming from Granta. So you can see here what the Young's modulus is, the Poisson's ratio. I've got some information about the strain life, the SN curve, and some more information there as well. Now, if we want to apply, some more, say, nonlinear conditions, some nonlinear, material properties to capture what's happening around there, because at the moment we've just got linear materials, right? We can go to our engineering data sources, right? We can come down to the general nonlinear material, and maybe instead let's just apply this aluminium nonlinear. You can see here what it's got. It's defined by the Young's modulus. We've got the Poisson's ratio, bulk modulus and shear. So this is all informing us about the linear properties. And we've got this bilinear isentropic hardening, right? So we've specified a yield stress, right? So we use the linear properties, the yield stress, determine what the curve is. And then we use the tangent modulus here, which is the gradient afterwards, right? So this bilinear model is appropriate if we have a little bit of yielding, right? So, and we can see what the plastic deformations might be. So let's go back to our material model here. Let's go to the model and refresh the materials. So we'll have the aluminium that's come in with the graph come through as well, right? So instead of structural steel, I'll specify it as aluminium. And we'll go back and start to solve the actual problem, right? So crack growth, no, that's we're not going to be looking at crack growth in this particular component. You can, though, if you want, have a look at, if you go to static structural, I think if you go to the fatigue up there, no. Might be in the nonlinear analysis. There, I think we've got an example or two about crack growth, but if you can't find it on the Learning Hub, there you go. So we've got some fraction material, some crack growth stuff there. Yeah, have a look through that or reach out to us, right? So with this, you'll notice again, total deformation. We've got some more stresses kind of around some of these regions. We can look at stresses around here, but notice now because we've got material plastic properties, the stresses around here look a little bit more appropriate. And if we insert, we can insert plastic strain, equivalent plastic strain. I can really pick up where we might have some plastic strain around this region, right? So previously, when we had that linear material, even though it was past the yield stress, we just gave it a pretty much the Young's modulus, which tells it, as the stress increases, as the strain increases, just give it more stress. But now that we've actually told it this is what the nonlinear portion of the curve is, we can have a look around that region and specify, all right, we've clearly got some nonlinear, we've got some plastic deformation around that region, and the stresses around here look a little bit more more appropriate as well, right? So around that region here, right? It's around 250. And then making that, you can start to make some design changes if you want to go through that process and start to fix some of that stuff up as well. All right. So that is just a quick run through about kind of setting up some analysis and then going through it. So we've also talked about having a look at the results. So we can apply things on a surface, by the way. So we can just select the surface. We can also, so similar to like we did before, we can select a line, and let's just say we want to look at what the total deformation is across that line. Actually, I know what I need to do. Instead of total, I want to specify directional deformation. Right, actually, let's just do it on the axes that we have over here. Right, so we can give it directional deformation. And there you go. So we can now show clearly, we can orientate by a certain specific axes. Instead of global, we'll use that coordinate system here. And you can see the Y is kind of coming across. So I'll select that over to Y. And I can evaluate the result. Not much is happening. We've actually fixed our conditions here, so that makes complete sense. We're probably not going to see much happening around either of these regions because we've gone in and applied a cylindrical support to those faces, right? But we can, let's just say we select this one over here. We can go to deformation. Rid of that. Go deformation. I just want that one edge. just that one edge there. Deformation along the Y, and we can evaluate that result. So you'll notice it gives us a value there, and it'll just tell us through the time steps, what the maximum value is. And if we convert it to path, right, what it'll do, it'll draw a path across there, and you can actually see the deformation over the actual path, right, starting from 1 to 2 in millimeters as well. Right. On top of that, I mean, if you instead of scoping the geometry, you can actually scope the elements if you want to as well. So you can actually highlight a couple of elements here, and again look at, say, your stresses on those particular elements. Right. So you can see what's happening through there, and similarly, you can again select a bunch of faces, pick up things like what the total deformation is on the element faces themselves. Right. So depending on what you're looking for and what you want to do, you can, scope however you want. Right. Change according to the mesh size. So Mohsin, just some questions. So the size of the stress area can be changed according to the mesh size. Yeah. So if you've got, depending on your results, right, you may not have the appropriate amount of elements to capture the stress and the stress gradient around this. You can see here we've got a couple of hot spots, which indicates you want to go back and make some changes and refine locally what's happening, because it looks like there's a pretty high gradient that just isn't picked up, right? So in these particular situations, these are unrealistic stresses. So that's why you want to go in and make some refinements to the mesh. If you're finding you're refining the mesh and it just gets finer and finer, you might want to have a look at things like your materials, which is what we've done, or your boundary conditions as well. They might not be appropriate, right? So how do you determine if it's a stress singularity or not? That's a good question. I've got a couple of things that you want to be considering, right? So sorry, we've got error. So stress singularity. So a couple of things that will give you some problems, right? So we've got crude geometry, right? If we're applying things to an edge, point constraints and point loads, right? What we're generally looking for is that, we think about stress is just force over area. As the area becomes very large, the stress starts to become very large as well. So that's what we want to look at. If we don't reckon we have enough, we want to go through and then do like an analysis where we start to refine around this region, like I did around here. And that's where you hopefully identify where the problem might be. And again, if the stress start to increase, we'll start to have some more as well. Sorry, does the video have sound? Sorry, can you not hear me? I'm guessing you guys can hear me because I've been responding to the chat comments. Yeah. Ryan, you might need to, maybe you can log out and log back into it if you can't find any sound on your current on Teams at the moment. Yeah, so hopefully, sorry Dan, that kind of answers your question. You want to look at, how you're applying the boundary conditions, how you're applying the loads. You want to look at the stress and the in reference to the mesh locally around that region, and you want to then start to make some refinements. If you're starting to see the stress just continues to go up, you'll probably want to look at your actual material properties and make sure you've got the appropriate material properties. You might find that you're actually yielding, right? So you're actually past the yield point, at which point you might need to apply things like a multilinear or a bilinear curve, telling the software, this is how the material will deform when it is plastic, right? So I guess one of the things that we can do, by the way, is, we're applying this pressure. If we say apply 2 steps, right? So let's apply, twice the amount. We know we've got some yielding around here, and then we'll go to 0 afterwards, right? So let's have a quick look at what happens with that. What we might start to see is that, when we load and unload it, we'll probably see we might see some residual stresses around some of those areas, depending on what's happening around there. You also notice again, if you're giving things like point loads, you look at like the energy or the results around there, you'll notice there are just there's a high amount of energy around that region, or stresses, or strains around there as well. All right. So let's have a look at the end. All right, so if we So we've got two load steps, right? So you saw there are two load steps here. And what's happening is the pressure is going up to 2 and then back to 0. If we look at the total deformation, so initially, initially nothing's really happening. By the end of my first load step is where I've applied all that pressure. You can see all of this deformation, right? 0.4 around there. And when I start to unload it, right, you can see I've still got some residual deformation. So it's a little bit around 0.1 millimeters. Again, looking at my stress, at the end of my first step is where I've loaded it. I've got quite a bit of hot spots, so I definitely want to go in and make the mesh finer before actually taking the results. But if we look, towards the end, we've got some strains here. We definitely want to go back and make some changes around some of these values. If we focus maybe around some of these regions where we know we've done some changes, again at the end of the first step when we've applied two megapascals, we've got 290, and then towards the end we've still got some residual stresses around that region. I'm sure if we have a look at our actual plastic strain, right, by the end of the first, we've got plastic strain around this region, and when we unload our object, right, again, we've still got some local strain around there, right? Everything else is okay, but locally around this region, we definitely want to go back and make some changes, right? So good. We can have a look through there. So you'll notice as well, one of the differences between this directional deformation is that it gives me the direction, right, and what the deformation is at a specific time step. Whereas if I was to go back, and let's just say I go back to here, I add that line again, and I've just got directional deformation in the Y, it will tell me over the time steps what is, as an example, what the maximum might be, right? So this is telling me what the maximum is over the time steps, whereas when I've generated a path, just delete that. When I've generated a path, it gives me the path and what the deformation is at a specific time step, right? So it's telling me at the bottom, at time step equals 2, at the very end, this is what the end result is looking like, right? So again, a couple different things that we can do around that region. Again, similar to before, we can look at stresses on elements, on faces as well. Nothing too special around there. Right? So hopefully that gives you a good understanding about how how we can identify a couple of these stress singularities and make some changes to the actual model as well. And then depending on the boundary conditions, you can really start to play around with it, right? Post-processing, yep, so I'm just going through what we've got. Oh, the other thing we can do is if you know roughly what the pressure is that you've applied, you can drag that over, or you can drag your supports over to the solution, and you can pick up things like the force reactions. It's always important for you to do that afterwards, right? We've got a pressure, which can make it a little bit difficult, but if we were to just go in and apply a force, we'll just give it a unit force, right? What we should be able to see is we should be able to see the force reaction again as a total and in the X, Y, and Z as well, right? So you can bring over your supports into the solution to pick up what the actual reaction might be. And you always want to be doing that. You also always want to be going back and double checking to make sure you've applied the correct constraints. Right. So we should be able to see that in a bit. And we've talked about, scoping them to different components. All right, so it's coming up on around 12. All right, so you can see there again, we've got our force reaction. It's coming up, being applied up until that, and we've got 100 reaction units. So that's exactly what we expected. All right. So these results will be a little bit different because I'm just applying force at the top, and I'm maintaining and keeping that load. All right. So force is simply being applied and maintained. Looks like this force is pushing up. So what we can do if we wanted to as well, so force is going up at 100. I've been talking about this, so I've been using these steps, right? So I can use multiple steps. If I go to this worksheet, you can see I've got 2 steps here. And what it allows me to also do is, is apply different loads in different time steps. So So let's just say I'm applying, 100 newtons up, but I want to apply 100 newtons in the Y condition on the second step, right? So what this will do, it'll apply 100 on both. When the second step starts to come in, we'll see some sort of deformation on the positive Y as well. Right, so we'll do a quick solve of that. So we can use the steps, we can do what's called a multi-step analysis, right? So we can apply things like bolt pretension, and then we can apply a force, then we can apply a load, and then we can, release it to see if there's any plastic deformation or any plastic strain from it as well. Right, so these are some of the things that we can do in the analysis settings. All right, so it's coming up to 12 o'clock. I think I've gone through most of the things that I wanted to talk about. I think some of the things that we haven't gone into too much detail about is in some of the sub-steppings. So if we just have a quick look, by the way, so we'll notice that, the first step, we've got force that gets pushed up. And then towards the end, we've got a force that's pulling it out. Right, so we're applying both up and then it's coming out. Right, and then again, you can look at things like your plastic strains and see what's happening around some of those regions. So it doesn't look like we've got any plastic strain whatsoever. And we can also have a look at the stress around some of these regions as well. All right, so it's around 20, so there's not a huge amount in this particular case. Right, so look, gonna finish up probably in like 5 to 10 minutes. I mean, is there any particular questions you guys want to answer? Maybe I want to take this time to go over any more questions that you guys might have. Hopefully it's giving you guys a good overview about how you can open up, start to think about your problems and apply appropriate loads and boundary conditions, thinking about if you need joints to connect things to the environment, or if we can get away with things like contacts as well, right? And then looking at the different boundary constraints and the loads and boundary conditions, you'll really need to decompose your particular loading condition and understand what's happening. How can I apply it? How is load being transferred from one component to the other? Do I have sliding? If I have sliding, do I want to allow separation? And you might want to think about your contacts as well. And then afterwards, after you've applied your analysis, you can then use your post-processing to look at results on the bodies, on specific faces, on specific edges. We can then graph them over time or graph them as a chart as well. There's a lot more things that you can do, but hopefully that's enough to get everyone started. And we've also talked about materials. So you can go into engineering data, find the materials that you're after, and you can apply them. If you have material properties, by the way, and you want to adjust the materials that are here, so if you go to the structural steel, if we go over to plasticity and we've got an isotropic hardening, we can include this property. It'll come up in here where you can then start to specify what the plastic strain and the stress might be, and it'll start to build the curves for you, right? Depending on your problem, by the way, you probably want to have a look at some of the material properties because we've got metals, but we've also got things like hyperelastic material properties, magnetics, geomechanics as well. And the models used can be very different, right? So if we have a look at the hyperelastic materials for a second. Sorry, the hyperelastic ones here. So you'll notice, for these like rubbers, right? There's different models that can be used. So in this particular case, right, using the Mooney-Rivlin model, we've got stress and strain, and there are other things like the YO, which requires more data, right? So it requires shear, biaxial, and unitensile, right? You've got all of those compared together, and that actually gives you the material properties of that component, right? Yes, the after the recording's done, I'll make sure to post it on the YouTube page, and links. I'll add a link to that as well. I'll try to make sure as well I send an email out to everyone from the CFD as well, and for the FEA going forward, that if they did miss out on any of the training, the information will be available via the YouTube link. right? And you can have a look at the, and if you go to the webinars, you go to the online training. If you want to have a look at some of the older training and the presentations, that'll also be able to, you'll also have access to all of that as well. Right. Awesome. Right. So look, we've got through quite a bit of information today. So we touched on and started to go over meshing in the morning. We then had a whole hour on contacts and setting up the connections, and then we had a whole hour on thinking about your loads and boundary conditions. We played around with the small model. Hopefully, that's given everyone a good idea and a good overview about what you can do with Ansys and all the different inputs and outputs that you'll need. So hopefully before starting your actual project, you'll be able to map out on paper, what material properties do you have? What are your joints, contacts, and connections? What are your boundary conditions? What have you been given, and do you need to make some changes to them? And how is your component supported as well? If you've got multiple bodies, how do these bodies interact? And what are you actually interested in, right? You look for your force, displacement, stresses and strains. Is it plastic? What material properties are appropriate? And if beforehand you can identify, where you might potentially have, constraints and where you've got stresses in your actual or stress concentrations, that's when you probably want to go in preemptively, going in and start to make some changes to the actual mesh, right? Refine around areas of interest. Make sure you've got, things like curvature and proximity turned on if you need to capture some of these conditions as well. If you start to have problems, again, you can use your local sizings, you can use your global sizings, and you've also got different methods as well. Some methods may or may not work, so it might be a bit of trial and process, or it might be going in and actually making some changes to the geometry, cutting them up, moving them around, and seeing what you can do there, right? Um, was it cable connections? Yes. All right. Thanks for that. I think we didn't get time to go over joints, but what we can do, I think I've still got that up, don't I? Yes. I will, so let's just create, so what I'll do here, I'm going to create a line body for this particular case, and we'll go back and make some changes and muck around with it a little bit later on. So I'm just going to make a profile here, so we can hit create, and what I'll do, I want to probably describe that. I want to line, probably go 3D mode, and we'll go from here. All right, a line that goes from there to the bottom there. All right, so we've got this line that we've created here, and I'll go into this connections here, and I'll give it a line body, and I'll give it a beam profile as well. So if I go back to this, I'm just going to get rid of these, and I'll get rid of these as well. Suppress that body, and we will bring in our geometry again. You'll notice now we've got an additional line body here, right? So by the model type, you'll straight away be able to pick up that we've got beams. We can also give it a link or a truss element, and you'll notice here at the bottom we've got a cable element, right? So we've got different components depending on what we're after. We've got to give it material properties. Now it's not connected at all at the moment, so we can use something like a joint, right? And that joint will connect the line body here to the the edge around that region, and we'll probably need to do exactly the same for the bottom. So depending on what you're trying to do, that's how you can potentially get that's how you can model a line element right between these two components. Let's see. I have a feeling I haven't set everything up properly, but let's just try. Let's just try and do this. So if we scope that to the outside, should be good. We've got a fix at the top there, and we've got a force at the bottom. Sure. Let's have a quick gander at the mesh. Got a couple of elements through there. We'll have a solve. I think this we need to have yet large deflection turned on as well. So we've got a couple of problems. Turned off. Yep. So we'll go into analysis here. Turn on large deflection. So large deflection recalculates the stiffness matrix on each one of these equilibrium equations. So every time we're solving and we're applying these loads, so we'll have a look at that. Run that. It looks like it's solving okay. Cool. So there you go. And that way, then now you can have a look at what the actual results are. Probably instead of true, we'll make this a bit bigger. You can see now, we've got this cable element. We've got this cable element picking up the deformation and taking the load between these two components there. All right. So Mason, hope that shows you how you can at least add a cable model to your component. So you want this beam here, and then we use joints in order to connect the edge, the point here to these edges. Apply our boundary conditions as is. We need to turn on large deflection, and then we can start to have a look at our results. All right. Awesome. All right, thanks, Jimmy. Thanks everyone for your time. Hopefully everyone was able to learn quite a bit from that. So tomorrow we're going to have Sam that's going to come in and walk you guys through the nonlinear training. He's going to talk about a little bit more about the nonlinear materials and some of the properties through there as well. I definitely recommend everyone to go through afterwards to the website, have a look at the structural fluids getting started, right? And at the bottom, run through some of the actual getting started material, right? So it talks you through and walks you through, meshing, loads, conditions, setting all of this up. If you go to the linear aspect of it as well, we do have some additional training material in here. A lot of this has, more material about how you can help you out and go through that process. Again, the linear materials will have the lectures as well, right? And some more videos underneath, right? So hopefully everyone is able to go through it and is able to learn quite a bit. And you've been able to learn quite a bit today. All right. Awesome. Thanks, everyone. Look, thanks a lot for your time. I'll end the meeting for now, and I'll make sure to send everyone an email, just letting them know where they can get the YouTube link for the videos in the future as well. Thanks, guys, and let us know on support, by the way, if you do need any help with any of your projects. Bye.